и почему-то не выведен на страницу МИАН.
Ну, это...
Вот есть на странице конференции, но почему-то не выведен на страницу МИАН. Так, все, ссылки на трансляцию все включились.
Вот, да, и пошла даже трансляция на YouTube.
А есть трансляция, да? Ну-ка, дайте-ка у меня. Сейчас, а если она на сайте? Вот проверять надо на сайте. Она там иногда... Вчера она что-то застряла. Почему-то не выведен. А есть, вот. На сайте Стекловки тоже транслируется.
Угу.
Так, ладно, это я закрываю. Ну, все, значит, у нас... Сейчас я открою себе, чтобы удобно смотреть было. Так, все готово к тому, чтобы начинать.
Ну, хорошо, тогда еще у нас 7 минут есть.
Да, у меня даже 8.
Ну, да, где-то 7-8, да.
Алексей Владимирович, все хочу вас спросить. Я вам написала после вот мемориальной
Да, не успел просто. Я
понимаю, что вам некогда. А вы как будете выкладывать фотографии?
Ну, я думаю, что я разошлю заинтересованным лицам такую ссылку, куда это все. Может, мне Пилюгин что-нибудь пришлет, как он обещал, какие-то видео. Ну, посмотрим.
Хорошо.
В общем, я думаю, что за несколько дней сделаю. Хорошо. Так.
Людмила Сергеевна, если вы немножко камеру опустите каким-то образом,
так, опустить, да? Вот
вы
так.
в кадре будете... Не, наоборот.
Наоборот?
У вас подбородок срезан. Вот так хорошо.
Вот,
Вот,
отлично. Да? Ага, вот так, да?
Как-то так, да. Там просто потом фотография будет на сайте, чтобы не отрезать кусок головы. Чтобы он не был отрезан изначально.
Ну, в общем, сейчас нормально, да? Все хорошо.
Хорошо. Так, ждем 5 минут еще.
Здравствуйте.
Здравствуйте.
Добрый день.
Здравствуйте, Людмила Сергеевна. Здравствуйте, Сережа.
Здравствуй, Ольга Витальевна.
Здравствуйте, здравствуйте.
А у меня, к сожалению, сейчас я не вижу почему-то тех, кто подходит.
А там надо какую-нибудь галерею показывать, галерею нажать.
Да, вот почему-то у меня эта кнопка пропала, я ничего не могу сделать, лучше не буду. Ладно уж.
Это правильно. Это дело ответственное, какие-нибудь кнопки жать. Ну, это верно. Так. Я пока тоже тогда себя выключу. Видео. Но я тут.
Хорошо, спасибо.
Людмила Сергеевна, а кто ведет секцию вашу?
А я не знаю.
А, не знаете? Да?
Я сейчас начну вместо Саши.
добрый.
Она добрый день. А она там, у нее какие-то срочные дела, я начну.
Все, поняла. Ага, хорошо, ладненько. Ага. Леш, привет. Здрасте, вам тоже здрасте. Угу.
Будем вовремя начинать или подождем чуть-чуть?
Может, а сколько там участников?
8 в сумме.
8, да? Ну, как организаторы сочтут правильным. Может быть, еще одну минуточку?
Ну, давайте минутку подождем.
1 minute. Угу. Чебуков добавил нам Городецкого на страничку Стекловки. Ну что, начинаем?
Давайте, хорошо.
Давайте, включайте тогда запись. Dear colleagues, let us resume our conference. Our first speaker for today is Lyudmila Yefremova from Lobachevsky State University and Cube Products and Geometrically Integrable Maps in the Plane. Please.
Thank you very much. Thank you. First of all, I would like to thank the organizers for the opportunity to deliver the talk at the conference devoted to the memory of Dmitry Viktorovich Anosov. It's the great honor for me, of course. And I plan to deliver the survey with the title that you see on your screens. And this survey
Людмила Сергеевна, прерываетесь.
Так, висит. Почему-то висит. Появилась запись, интернет-соединение неустойчиво. Так. This is the survey from main ideas in the study of skew products of interval maps and the key decomposition theorem for the space of C1 smooth skew products of interval maps with a complicated dynamics of the quotient maps to current results on periodic behavior of continuous integrable maps. And our last remark deals with the generalization of two-dimensional Lorentz maps and its periodic Lorentz maps and their periodic orbits. And there is a rich literature and the rich history devoted to investigation of skew products dynamical systems of different classes. This conference confirms this claim. And I would like to distinguish only one series of papers by Dmitry Viktorovich Anosov and his former PhD students. These papers were published in 70s years. In the first paper, Dmitry Viktorovich observed in particular that results on topological, then his former PhD student Sidorov proved the existence of topologically transitive analytic cylindrical cascades that have non-empty set of intransitive points. His other PhD student, Krigin, solved the Poincaré problem on the structure of omega limit sets of cylindrical cascades. And some years later, he investigated the influence of the property of smoothness of cylindrical cascades on the structure of omega limit sets. I add here the famous paper by Dmitry Viktorovich that is called Dynamical Systems in 1970s, the Hyperbolic Revolution. This paper contains some problems on the study of dynamical systems of skew products class. The approaches of this paper are close for me. Therefore, in October of 29th, I went to Dmitry Viktorovich to ask him to be the scientific supervisor of my probational period. I didn't wait, but he agreed, and really, he was the scientific supervisor of 2 my probational periods. It was short time, but his influence on myself was huge, and it makes it possible to finish in the work on Doctor of Sciences thesis. And this thesis were presented at the Institute of Information Transmission Problems. And during this presentation, Anatoly Mikhailovich Stepin told us that in the last year of his life, Dmitry Viktorovich charged Anatoly Mikhailovich to help me and support me and on the last steps of preparations of Doctor of Sciences thesis. And this is fulfilled, but there are no now Dmitry Viktorovich and Anatoly Mikhailovich. But the memory about this outstanding persons is with me. And let me go to results on the skew products of interval maps. We consider a map of type 1 with the phase space with the closed rectangle I as its phase space. The dynamical system connected with the map 1 is the pair of autonomous dynamical systems on the unit interval I, on the interval I sub 1, and the second one is the non-autonomous dynamical systems, which is defined on the closed interval I sub 2 for every x from I sub 1. And if we continue every iteration of skew product F large, then we see that we can present this skew product as the composition of two more simple maps. The first of them is the skew product with the identity quotient, and the second map is the direct product with the identity fibers maps. And as we see by this presentation, every iteration of F large can be presented as the composition of the map F sub 1 and F sub n and 1. This is important for the further investigation of skew products dynamical system. The main problem that was solved in that time is the description of the non-wandering set of skew products of interval maps. And on this way, the concept of the omega function of every continuous skew product was suggested. And we consider the multi-valued function that is defined on the non-wandering set of the quotient F small, and its value in every non-wandering point coincides with the slice of the non-wandering set of the map F by the fiber over the non-wandering point X of the quotient. By the slice, we mean the projection, the second projection of the section on the axis OY. And I consider this approach as the adapted version of Poincaré idea, who suggested to study the structure of omega limit sets using the sections of these sets by generators of the cylinder. And here we obtain the functional approach to the study of the non-wandering set. And this function is upper semi-continuous. Therefore, we obtained some information on the topological structure of the non-wandering set. And as for dynamical sense of this function, then its graph coincides with the non-wandering set of a skew product in the phase spice I. And it's not enough for the study, for description of the non-wandering set. Therefore, two functions, f sub n, this is direct product with the identity quotient, and the other function, f sub n and 1, with the identity fibers maps, make it possible to introduce other multifunctions. These multifunctions will be used in the composition of the space of C1 smooth skew products of interval maps, and other functions will be used for description of the non-wandering set. The first of these functions is an auxiliary multifunction of a skew product that is defined for every natural number n. All these functions are defined on the non-wandering set. We see here the condition about complete invariance of the non-wandering set of the quotient. I would like to recall here that if we consider endomorphism, then the non-wandering set is invariant only in the sense of inclusion. And every auxiliary multifunction of a skew product is defined by the following equality. Its value in any non-wandering point of the quotient coincides with the non-wandering set of the fiber map G sub xn of the nth iteration of f. But these functions have no real dynamical sense. But if we consider the closure of the graphs of auxiliary multifunctions, then we obtain so-called suitable multifunctions for the omega function, and the values of these multifunctions in every non-wandering point of the quotient is presented here. Our decomposition will be based on the correlations of properties, continuity and discontinuity, auxiliary multifunctions, and suitable multifunctions, also on these properties of the omega function. And then it is important to note that having defined auxiliary multifunctions and suitable multifunctions, we stopped the motion in the base. Therefore, every point from the graph of auxiliary multifunction or suitable multifunction must move to the point fn of x, y. And this problem can be solved with the use of direct product f sub n and 1. And this function is called approximating multifunctions, and the equalities that define the values of these multifunctions in every non-wandering point of the quotient presented here. And if we consider maps F large, the skew products F large, such that their quotients have a finite number of preimages, it's some restriction on the properties of the quotient, then it's necessary to note that the properties of continuity or discontinuity of approximate multifunctions coincide with the analogous properties of auxiliary or suitable multifunctions. And using topological upper limits on some subsets of the non-wandering set of the quotient, we describe the structure of the non-wandering set. But I will not say about the exact formulas for description of the non-wandering set. Our main goal is to present the decomposition theorem for the space of C1 smooth skew products of interval map. Therefore, I must say that the properties of the quotient and the properties of fibrous maps, of course, play an important role in the description of dynamics of skew products dynamical systems. Therefore, I would like to recall the famous Sharkovsky's theorem for coexistence of periodic orbits of continuous interval maps. And I would like to mention here that the generalization of this theorem on the case of skew products on n-dimensional cells was obtained by Peter Claudon in 1979. And this theorem makes it possible to to decompose the set of all contiguous maps of a closed interval into itself on three important subspaces. One of them is the subspace of maps of type less than to infinity. That is the space of maps that have periodic points of the bounded set of least periods. These periods, by Sharkovsky's theorem, are degrees of 2. And the second subspace consists of maps of type to infinity. Then the maps of this type have periodic points of all periods of degrees of 2. And our main attention will be at the subspace of maps of the type greater than to infinity. This is the maps of this type have complicated dynamics and it means that the maps of this type have periodic orbits of least periods different from powers of 2. And then as we see, the properties of the quotient map have the play an important role in the study of dynamics of skew product. Therefore, we use omega stable in the space of C1 smooth maps of the closed interval I sub 1 into itself with the invariant boundary. And as we see, the maps of this type don't contain the subspace of maps of type to infinity. And in the case of maps of type less than to infinity, the structure of non-wandering set is simple. And in the case of the maps with quotients of type greater than to infinity, the non-wandering set can be presented as the union of non-empty rarefied part and non-empty perfect part. The perfect part consists of a finite number of locally maximal, quasi-minimal, hyperbolic, perfect, nowhere dense sets. And if we want to obtain the distribution of the set of C1 smooth skew products of interval maps with the omega stable quotients, then and we use the properties of continuity and discontinuity of corresponding multivalued functions, then we consider then in any isolated point, every function and multi-valued function in particular is continuous, and the discontinuity points can be observed on the perfect part of the non-wandering on the perfect part of the non-wandering set of the quotient. And then as it follows from my previous words, our distribution is based on the using of sequences of suitable or auxiliary functions, and we don't need in all functions in all these functions for every n. We use only recurrence times for the non-wandering points of the quotient. And these times are well known from one-dimensional dynamics. And as we see, these times coincides with the least periods of periodic orbits that exist on the perfect part of the non-wandering set. And here you see the formulas for recurrence times for trajectories of all non-wandering points that belong to the perfect part of non-wandering set of the quotient. And then let us list all possible logical opportunities for every skew product for every C1 smooth skew product with the omega stable quotient with the type greater than 2 infinity. The first subspace is of these maps is the subspace where every skew product have a sequence of auxiliary functions with the recurrence times that contains not greater than a finite number of discontinuous functions. The second space has no common points with the first subspace, and we say that a map F large belongs to the second subspace. Then the sequence of auxiliary functions of this map contains countable number of discontinuous functions, but the sequence of suitable functions contains not greater than a finite number of discontinuous functions. And if we say that a skew product belongs to the third space, if the sequence of suitable functions contains a countable number of discontinuous functions, and F large has continuous omega function. And the fourth subspace is the subspace of maps such that every skew product from this subspace has the sequence of suitable function that contains countable number of discontinuous function, and F large has discontinuous omega function. This list contains all logical possibilities for considering skew product of interval map. But therefore, the decomposition theorem is the existence theorem for maps in every subspace. This theorem claims that each subspace, each distinguished subspace for all I from 1 to 4 is non-empty, and these subspaces are pairwise disjoint, and their union coincides with the part of the space of C1 smooth skew products of interval maps with the omega stable quotients of type greater than to infinity. Due to this theorem, the structure of the non-wandering sets for maps in every subspace was described, and this theorem is the key for different other results, and in particular for description of every subspace. But if we have some information for the first and fourth subspaces, then I have no information for second and third subspaces. This is the first part of my talk. The main result of the decomposition theorem is presented in these two papers. This part is based on these papers, And let us begin to the second part of my talk. Although there are many deep unsolved problems for this simple, it seems that for these simple skew products in two dimensions, nevertheless, I think that it is necessary to begin some generalizations of these considerations. And I see here two ways. One of this way is to increase the dimension of our considerations, and the other one is to consider the more wide class of maps than skew products maps. And two outstanding persons, Rostislav Grigorchuk and Vladimir Belich, independently from each other, in different time, attracted my attention to investigation of maps that is called geometrically integrable maps. And so let us consider a self-map G on the curvilinear trapezoid, which is described in this part of the presentation. And let us consider a G invariant subset of pi. And if there exists a self-map psi on an interval J of the real line, and psi invariant subset B of psi, such that the restriction of G on A of G is semi-conjugate with the restriction of psi on B of psi by means of a continuous surjection, then we say that a self-map G of pi is geometrically integrable. And I would like to recall that restriction of psi on B of psi is said to be the quotient of the map, of the restriction of map G on the set A of G. And this definition is, in this definition, a self-map G of pi can be continuous or discontinuous, single-valued or multi-valued. And the idea of this definition was suggested by Rostislav Grigorchuk, who introduced this definition for rational or in particular polynomial maps on the projective plane. And in the definition by Grigorchuk, there is the property of continuity of the surjection H. But if we consider the wide class of maps, then we add here the continuity property of the map H large. And this concept was forming in the pages that you see on your screens. And further, then I should give examples of integrable maps. And of course, the first example is a skew product on of interval maps on the closed rectangle in the plane, and this map is semi-conjugate with its quotient f small by the first natural projection. The great list of integrable maps in projective plane is one can find in the recent paper by Dank, Grigorchuk, and Lubitsch. And in these two examples, the property of integrability is fulfilled for considered maps on the whole phase spaces. But in example 3, we give the map such that this map is integrable on the invariant part of his phase space. This map is integrable on the interior of triangle delta. I would like to say that this map is topologically conjugate to Lotka-Volterra map, and the topological conjugacy is so that Lotka-Volterra map is integrable on the fourth quadrant of the plane. A very interesting example we obtain if we consider perturbations of skew products. And in recent papers, one of them is fourth paper. One of them is fourth paper. It's not fourth. It's a ninth paper. It's ninth paper. And in the paper that was published in Journal of Difference Equations and Applications, the maps of this type were considered. This is a wide class of maps. These maps without property of the smallness of function mu contains an NO map, and we consider the maps for under the following conditions. These maps are C1 smooth, have invariant the rectangle J square has invariant boundary. The function mu satisfies zero boundary conditions. And here, very important, the property of omega stability of C1 smooth self-maps. In the C1 smooth self-maps of an interval J with the invariant boundary. And then the property of smallness of function mu is correlated with the property of omega stability. And then the criterion for geometric integrability for considering map is obtained in complement condition that the phase space is compact set, and we have some restriction on the continuous map H. We suppose that this map is a bijection of every horizontal fiber. Is a bijection of the slice of our set by every horizontal fibers on the set B of psi. Then under this condition, a map G is integrable if and only if the set A of G is the support of a continuous invariant lamination, if the closed set A of G does not equal pi, or continuous invariant foliation, if A of G equals pi. And under our conditions, the topological structure of fibers are very simple. These fibers are graphs, are pairwise disjoint, graphs of continuous functions that are defined on the closed interval J sub 1. The key property here is the invariance of this foliation or lamination. And then after this geometric criterion for the integrability, the analytic criterion for the integrability was proved. This criterion means that under some conditions that were mentioned above, every integrable map is reducible under the homeomorphism to a skew product of type 7. We see that the quotient of this skew product coincides with the quotient of integrable maps. And fibrous maps have the following type, where these fibrous maps considered in shifted point of the interval J. And this is very important property that means that there is a deep relation between integrable maps and skew products dynamical system. Skew products dynamical systems. I would like to point out one correlation else. Let us consider an integrable map with two coordinate functions, g sub 1 of x, g1 of xy and g2 of xy, and consider the one parameter family of skew products that are defined on the variable closed rectangle. Here the base j sub t is the set of x such that the points xy belongs the phase space. And then we see by definition of these two maps that the integrable map and skew product for every t from j prime coincides on a horizontal fiber g sub t, direct product of g sub t and t. And it means that we obtain the opportunity to find the value of every point from the phase space under the nth iteration of f. This formula shows us that autonomous discrete dynamical system generated by an integrable map equals the non-autonomous dynamical systems generated by the family, one parameter family of skew products dynamical systems. There are many other correlations, but I plan here to consider the coexistence periods of periodic points for integrable maps. It was a surprise for me because the integrable maps admits the generalization of cycle coexistence periodic that these periods of periodic orbits admits the description using the Sharkovsky's order. Therefore, we obtained here the generalization of Sharkovsky theorem on the very interesting class of integrable maps in the plane. And this theorem is formulated for the closed invariant subset of the phase space under some complement conditions. And here you see the corollary of these results that is formulated for periods of periodic orbit for maps that are integrable on the whole phase space. And further, I would like, and my last remark deals with generalization of Lorentz two-dimensional maps. I would like to address on the paper by Anushich, Bruin, and Chinch that was published in the same journal of difference equations and applications. And this issue was devoted to the birthday of Alexander Nikolaevich Sharkovsky. And there he considered the one-dimensional Lorentz maps derived from symmetric unimodal maps. Here you see the definition of symmetric unimodal maps, and we can define increasing symmetric Lorentz one-dimensional Lorentz map and decreasing one-dimensional Lorentz maps, and Lorentz map. Here you see a graph of an increasing one-dimensional Lorentz map. There are many works devoted to the periodic behavior of one-dimensional discontinuous Lorentz maps. I mean works by Rand, Hofbauer, Alceda, Lebrand, Misurevich, and it's my pleasure to say here that the properties of these maps were studied from other points of view, were studied by and now are studied by my colleague Mikhail Malkin. And here I would like to recall the theorem presented by Anushich, Bruin, and Chinch, and he proved that symmetric increasing Lorentz maps satisfy Sharkovsky's theorem, except for the fixed points. As we see on this picture, this map have no fixed point. And if we consider decreasing symmetric Lorentz maps, then these maps satisfy Sharkovsky's theorem, possibly except for periods of powers 2 for degrees that are not less than unit. And this theorem gives a nice form for presentation of periods of periodic orbits that exist in symmetric increasing or decreasing Lorentz maps. And now I would like to give the definition of generalized two-dimensional Lorentz map. A map G defined on a compact trapezoid pi is said to be 2D is said to be the generalized 2D Lorentz map if its second coordinate is continuous, or if its second coordinate is discontinuous on both variables x and y, and its quotient is a one-dimensional Lorentz map. And it is interesting that for description of periods of periodic orbits of integrable maps of type generalized 2D Lorentz maps, we use only the continuity property on the second variable for description of periods of periodic orbit. And it was proved that under our standard conditions on the map H, we generalize the result by Anushich, Bruin, and Chinch on the generalized integrable 2D Lorentz maps with with the quotient that derived from symmetric unimodal maps. And moreover, such map contains periodic points of every least period n, where n precedes m, where m is given period of periodic point in Tchaikovsky order, possibly except for n equals unit, if psi is symmetric increasing Lorentz map, and except of powers of 2 if psi is symmetric decreasing Lorentz map. It is interesting that in two-dimensional case we can improve the description of periods of periodic orbits in the case when the quotient is decreasing symmetric Lorentz map. And here it's the last part of this theorem. We see the necessary and sufficient conditions for the existence of periodic orbits of periods of degrees of 2 for this type of maps. And my last remark, the considerations connected with the considerations connected with generalizations of Tchaikovsky's theorem are considered in this paper with my former PhD student, Elena Makhrova. Thank you very much. I finished.
Thank you. Are there any questions or comments? So no questions, no remarks. If not, yet let us thank the speaker.
Thank you.
So, and we have a break, 10 minutes break till 2 p.m. Moscow time.
Сергей, можете попробовать. Ага.
Сейчас, да, вот я попробовал так, видно, да?
Видно, да. Можно попробовать на весь экран развернуть.
Да, сейчас я это хочу сделать. Так, не совсем так. Так вот так вот это делается, да.
Хорошо, тогда ждем 10 минут.
О, привет, Сережа.
О, привет, привет. Привет, Миш. Да.
Значит, ты сейчас в Польше работаешь, да?
Да, в Польше. Польша сейчас.
А что у тебя за позиция там?
Ну вот политехника Гданьская, я там профессор, ну, научный работник скорее, ну, довольно сложно. Тут польская система не совсем переводится ни на русскую, ни на французскую.
Понятно. Ну, ты сохраняешь свою позицию в Петербурге, да?
Ну, у меня четверть ставки у Стаса на факультете есть, то есть я там читаю даже какие-то курсы онлайн. Ну, основная здесь, но, в принципе, сколько-то есть и в Петербурге.
Понятно, хорошо.
Ну, пока меня оттуда не гонят. Ну, не знаю, как оно будет. У тебя все по-прежнему?
Все по-прежнему, да.
Ясно. Ну, так, пока обживаюсь. Я только у меня получилось приехать только в начале октября,
Угу.
где-то месяц примерно. Все с пандемией не так просто, как понимаешь.
Угу. Понятно.
Добрый день, Сережа.
Добрый день, Сергей Юрьевич. Сергей Юрьевич,
Алексей, вам добрый день, конечно.
Сергей Юрьевич, я вас попрошу, тут я буду некоторые исторические вещи рассказывать. Если я не прав буду, поправьте меня, пожалуйста. Потому что это про то время, про которое я знаю не очень много и могу ошибаться.
Здравствуй, Сережа.
Здравствуйте, Владимир. Здравствуйте.
Рад вас видеть. Это очень приятно вообще. Если есть что хорошего в таких конференциях, что можно увидеть неожиданно Сережу Крыжевича.
А можно и Славу Гриниса?
Спасибо.
Ага, и Славу Гриниса, да.
Славу Гриниса можно увидеть.
Очень рад
Да.
вас видеть, Владимир.
Это кто там про Славу Гриниса? Сережа, я рад тебя.
Да.
Да, тебя не выпускает из дома. Ну, вообще в парк-то можно сходить погулять?
Можно, но я вместо этого сейчас вот лекцию читал
Понятно. Нет, надо сказать,
про
работать
линейную
тяжело.
независимость
Олег, пора
квазиодночленов.
начинать. Пора
Так
начинать.
тяжело онлайн работать, это вообще. Здравствуйте.
Добрый день.
Ага, очень
So,
приятно.
dear colleagues, let us resume our session. Our next speaker is Sergei Kryzhevich from Gdańsk University and St. Petersburg University. The talk is about structural stability for dynamical systems on time scales. Please.
Thank you. First of all, I would like to say that it's a great pleasure and great honor for me to make a talk here. And the special pleasure is that the conference is devoted to the memory of Dmitry Viktorovich Anosov, who is a positive example for me as a scientist in many aspects. And I would like to start with some results about structural stability for non-autonomous systems of ordinary differential equations. And probably the story started in late 70s. Then my, at that time, future scientific supervisor, Professor Pliss, was in the United States for a year. And there, and Dmitry Viktorovich Anosov was also there. And they had a chance to communicate. As usually happens, people living in different cities, they meet in another country. And I don't know if the results by Professor Pliss, which I mentioned later concerning structural stability of non-autonomous systems, were inspired by communication with Dmitry Viktorovich Anosov, but somehow they just followed this visit, and it's very likely that it was inspired by communication with Dmitry Viktorovich. So let me start with very classic results about structural stability. If we have a diffeomorphism of a smooth compact manifold, and if the diffeomorphism satisfies axiom A, then, as everybody knows, the omega, the non-wandering set can be decomposed into a union of disjoint basic sets. And if, in addition, the strong transversality condition is satisfied, then the diffeomorphism is structurally stable. The result, which was first proved by Rodin in 1971 for C2 smooth maps, and then it was boosted by Clark Robinson, who also proved the similar result for flows. However, none of the numerical systems of ordinary differential equations are also very interesting and very useful in many aspects. And of course, it was also interesting, what can we say about non-autonomous systems? You cannot reformulate the statement directly, since axiom A is something about periodic points. And if the right-hand side of the system of ordinary differential equation is not periodic, then you can hardly expect that there are some periodic solutions, and even if they are there, they are not significant for the dynamics. So, so you should think you should try to manage with some other properties, and so let me give you an idea what happens in this case. So we study a system of ordinary differential equations in Euclidean space, and for this reason we have to, since the space is non-compact, we assume that the right-hand side is bounded together with its derivative over x. And so let this be a solution with initial conditions x of t0 is x0. And given a small perturbation, we try to find conditions such that the perturbed system has a solution which is for any solution x of the initial system, there is a solution of the perturbed system which is close to initial one, and if possible vice versa. So first of all, I would like to mention the results of my old paper with Professor Please. It was the paper of 2003. So I recall the definition for hyperbolicity of non-autonomous systems of differential equations. So for every t, there is a decomposition of Rm into stable and unstable components, and the action of fundamental matrix shrinks the vectors over the stable components and shrinks the vectors of unstable components in negative direction exponentially. So what was the idea which belongs to Victor Alexandrovich Please, to how can one reformulate the axiom A for non-autonomous systems? So it is possible to consider linear parts of the given initial system in neighborhoods of its solutions. So this is system 1.3. So this is initial conditions for a solution, and like this we can linearize the system in a neighborhood of every specific solution. And it was assumed that for any x naught, there are such time instants, a finite number of time instants, such that these time instants depend on the choice of x naught, this linear part is hyperbolic on every of those segments, tau j plus 1. Besides, the dimensions of stable spaces increase, and these spaces intersect transversally, and the angles between them are uniformly bound. So the first question is, where is axiom A here? If you look at the dynamics of axiom A diffeomorphism, the solution behave like following. If they don't belong to a basic set, so they start near one basic set, and then they pass neighborhoods of several basic sets. Then they can stay. Well, first of all, they only spend finite number of iterations out of neighborhoods of basic sets, and so they travel from one basic set to another one and never come back. And so the majority of their dynamics is something which is spent near basic sets where the dynamics is hyperbolic. And so in this sense, those segments tau j plus 1 is an analog of the time that a solution spends near a particular basic sets with a given dimension of stable manifold. And this condition 3 is just the strong transversality condition. And moreover, wow, of course this I say that these systems are hyperbolic on segments tau j plus 1. If those segments are finite, then any system is hyperbolic on a finite system and on a finite segment, sorry, and there is nothing to say. But here it is very significant which are those constants of hyperbolicity, namely these constants A and lambda. So it is assumed first that these constants are the same for any solution and any segment, and then those segments must be long enough. So precisely, it means that this T capital is the minimal length of those segments where the systems are hyperbolic. And alpha is a lower estimate for angle between stable and unstable spaces. And there are two technical assumptions on T and A, which must be satisfied. And and now I'm able to formulate the main result of our paper with Viktor Alexandrovich. So if the nonlinear system, non-perturbed system, satisfies condition 1 and 3, 1, 2, and 3. So let me show it once again. And also the parameters T, tau j, the distance between the length of those segments is bounded by T capital. Then for any epsilon, there is a delta such that there is a homeomorphism which maps initial conditions of a solution for initial system to initial conditions of the solution of perturbed equation, and those solutions are epsilon close. So this is So this is a little, this can be treated as a kind of shadowing for non-autonomous systems, but it's a bit more, because in this case, we provide a one-to-one correspondence between solutions of non-perturbed systems and those of the perturbed system. So, wow, it's a bit less than inverse shadowing, but a bit more than inverse shadowing plus direct shadowing, and a bit more than just direct shadowing. Since I mentioned those results, so I have to say that this result just without statement of there is a homomorphism phi was obtained by Viktor Alexandrovich actually much before. So which means that for any x of t, there is y of t, the solution of the perturbed system, and it might happen that there is one solution y which corresponds to infinitely many solutions x. So this is actually classical shadowing result. However, here I have to say that Viktor Alexandrovich himself was quite reluctant in using this kind of terminology, and so here is the list of his papers where he obtained this kind of, say, shadowing. And here I must say that, of course, this is not the only result on shadowing for non-autonomous dynamics. And of course, this theory is quite well developed. I just know two recent papers. The second one is very general, so it deals with infinite dimension spaces and so on. And besides, it contains a brilliant, so this paper I mean by Lucas Bakes and Davor Dragicevich, sorry. And it contains a very good review. So yeah, it contains. So, and besides these two names, of course, this theory was. There were many other scientists who made a great contribution to this theory of non-autonomous shadowing. I should mention Sergeyevich Perugin, Kenneth Palmer, Sergei Tikhomirov, Kazuhiro Sakai, and actually there are many other people who made a significant contribution to this theory. And now let me say a few words about the idea of the proof of the mentioned theorem. So how it is proved. So the first idea is it was how we reduce, how we can improve the C2 result into C1 result. So this idea belongs to Robinson, and we just take small cubic neighborhoods of point x0, and we average those right-hand sides, those linear parts, matrices of linear parts over these cubic neighborhoods. So we do it so that these matrices start depending smoothly on the variable x0. And then, well, what is the main trouble in proving that there is a diffeomorphism? Once again, so if we study this system, then you consider those linear parts, and they are hyperbolic over finite intervals. but it's really difficult to find the canonical interval, well, specific interval, and also you have a certain freedom in selection of stable and unstable spaces. And having this uncertainty, you can hardly specify solutions, bounded solutions of this system. So if we have a hyperbolic system over a real line, you have only one solution for a non-uniform system of ordinary differential equation. If you add kind of f of t to the right, then you have only one solution. In this case, if you have a finite interval of time, you have many bounded solutions, and the problem is how to select one. So the idea was to move all these tau as much to the left, take them as small as possible, so that those systems are still hyperbolic with constants 3a and lambda divided by 3. So well, if you if you take this averaging, then you spoil these constants, and they are already worse, say 2a and lambda over 2, and then you shift all these constants so that the system is still hyperbolic with these constants. So like this, you can specify this tau j, and then you can use a formula, an analog of Perron formula, to find the bounded solution of this system over those segments. And the main question is how to stitch bounded solutions, define it on different segments, tau j plus 1, and this is so this is done like following. So you have a stable manifold of a solution on the step j plus 1, and unstable manifold of the solution on the previous space, and you just take intersection. Sorry, not manifold space, stable space, because we deal with linear systems. And then, you can find bounded solution for this system, provided the stable and unstable space are specified. But still, you have a freedom to select stable and unstable spaces on bounded intervals. So you have some set of admissible stable and unstable spaces. You can treat them as points of Grassmannian manifold, and you just take average over Grassmannian manifold for this over these possible stable and unstable. And like this, you can finally find the linear operator which puts into correspondence to the function f and to the function f on the right hand side a bounded solution of a given system. And then, having this, you can you need to prove that those operators, which is not evident, by the way, you need to prove that they continuously depend on the point, that they are uniformly bounded. And after we do this, we can consider Perron's method of successive approximations. So you can take on every step you can consider this kind of linear system, second line, and then you can find bounded solution, and like Perron proved his theorem, you can say that these approximations, they converge, and like this you obtain the solution of the perturbed system. So this is how the result can be proved. And now let me proceed to the second part of my talk, which is dynamical systems on time scales.
Seriously, excuse me, may I ask a question? Maybe it is a stupid question. So
Yeah.
about hyperbolicity on finite intervals,
Yes.
So
Yes.
If I understand correctly, there are many possible ways of choice of stable and unstable subspaces on finite intervals, and you make
Exactly.
sort of, and you can make sort of average, and these are these averages which are EJ from your transversality, from your theorem about.
Yeah. Okay. So there are indeed there are many ways to choose to select stable and unstable spaces, and so well in anyway, whatever you choose on the step, say 1 and step 2, those spaces will intersect transversally, because well it's the segments are long enough, and well all the variance is concentrated on a small neighborhood in Grassmann and manifold. And so for any choice, so you have so any choice of your stable and unstable spaces is just a point on a product of Grassmann and manifolds.
Mm-hmm.
And and there is an operator, which there is a specific operator of sorry, where it is, of this kind, Gothic, yes, which gives a bounded solution. And then I average not stable spaces and subspaces, which is a non-trivial procedure, but I average those operators. So I just take a measure on a space of all admissible. There is a Lebesgue measure on a Grassmann and manifold. The space of all admissible stable and unstable spaces has a non-zero measure, because the interior is non-empty, and so I can just take average with respect to the Lebesgue measure. So did I answer your question?
More or less, okay. Thank you.
Okay. So and now let me proceed to the second part, which is time scales. What is this? This is an attempt to generalize both discrete and continuous dynamics. So you can, for example, you can think of numerical methods with non-uniform step, or you can just think of so sometimes you consider a system which is sometimes continuous. So you just have ordinary differential equation, and then it has some jumps. So why it is important to study? In some cases, you have strong nonlinearities, like impacts, Coulomb friction, and so on and so forth. And these kind of black swans in economic models. And then you study these numerically. You need to have more precise calculation in the neighborhood of the points where the strong nonlinearity is there. And you can relax, so just, well, sometimes if you have, for example, a linear system with impacts, you can just solve it between impacts, but you still need to apply this condition in the neighborhood of nonlinearity. So there are some systems which are solvable on several intervals of times, and they admit numerical solution only on some other intervals of times. And this is the main reason to introduce this hybrid type of systems. So you have the time scale is unbounded closed subset of R, and the grindiness is just well, if you have a point, then it's the distance to the next point, which is 0 if you have no gap here. So this theory was quite well studied in the last 2 decades, and so the calculus and analysis was introduced for these time scales. So, for example, there is the so-called delta derivative introduced. So, which means that just simple Taylor decomposition is there. So delta derivative is gamma. If the following is satisfied, you can easily check that it's just regular derivative if the time scale is a line or a segment, and you consider interior point of this segment, and this is just difference between the values of the function divided by distance between arguments of these functions if we have a discrete. Of course, these time scales are not reduced to those kind of discrete and continuous. There might be countersets and something worse, but still. So, and also it is possible to define integrals, or they called antiderivatives, and you can consider. So there is I just skip the long list of references, which can be I can go back to it if necessary, and you can consider systems of differential equations on time scales. So what is important there, that if you don't have a periodic time scale like line or natural number or integers, then you cannot, even if you have a phenomenal system of differential equations, here it is linear, but I'll deal with nonlinear systems as well. So you cannot treat them like autonomous systems because, well, for example, if the time scale is not periodic, you can hardly expect existence of periodic solutions. Well, for this case, of course you have a solution x equal to 0, but still. And there are other unpleasant phenomena that can be there. I forgot to say this. Yes, you should deal with the so-called regressive functions, so that for example, you should avoid phenomena like this. If you consider this kind of system, so which means that it just corresponds to xn plus 1 is xn plus xn plus 1 minus xn. So you just, any solution falls to 0 in one step. Of course, this should be avoided, and this is why this is a technical moment which is impossible for ordinary differential equations, and this must be avoided. And so, yeah, okay, I have some time. So the stability theory for linear differential equations was developed, and so this is the analog of exponent on time scales, a bit specific, and some analogs of Gronal-Bellman equality were proved for time scales, and so the stability theory based on Grunwald-Bellman approach can be developed, and there are many brilliant papers related to this aspect of stability theory. Also, there is an approach to stability theory for timescale systems based on Lyapunov functions, and it's also there. So, well, this is in terms of linear systems of linear non-autonomous systems. You can introduce upper functions and upper exponents and use them to prove, like, for example, Milyonchikov-Bulov-Izobov theorem for linear system. You can prove stability, structural stability for linear system. Well, namely, for example, if the system is stable, then you add a small matrix, and if it is stable, and so you can say if it is stable or not. So the Milyonchikov-Bulov-Izobov theory can be translated to the language of timescales. And yeah, so here. There is one important thing I should also say, that there are some exotic time scales where solutions of systems with bounded right-hand side cannot have positive or negative Lyapunov exponents, only zeros. It can happen if the time scale is very, very rare. So 2 power n. So if the gaps are huge, then you cannot expect exponential growth of solution. The idea is, but these examples are kind of exotic. However, given a time scale, given a system of time scales, you can in fact introduce a system of ordinary linear system on time scale. You can introduce the system of ordinary differential equations, which is equivalent to this system. So this means that if you take a fundamental matrix of the second system and take a restriction to the time scale, which is a subset of R, you just get a fundamental matrix of this system 7. And this is a great tool which makes it possible to translate all the results of the system in time scales into the language of non-autonomous systems of ordinary differential equations. For example, you can just specify this embedding of timescale dynamics into regular one, and you can say that this system is hyperbolic if this system is hyperbolic just in a classical sense. Oh wow! So, and moreover, you can translate Lyapunov-Perron theorem on conditional stability into the language of timescale systems, and even you can introduce these Perron approximations, just bounded solutions of these systems. So there is a translation. There is a translation which allows to prove Perron theorem. However, it must be said that in some cases it does not explain. This hyperbolicity is a bit fake in some cases. For example, here, for this time scale, you don't have any hyperbolic systems at all. So, for example, if you have real line, it's okay. If you have integers, it's okay. But if you have very rare time scale, then this result is void. So you don't have any system to apply this result. But still, by the way, still you can speak of some kind of stability, but yet I don't know how to deal with it. And so what can be done? You can also, which is quite new, you can also translate this result on structural stability I've mentioned. You can literally translate this approach to the language of time scales. So you can, so if you have a system, as well, this result is actually about, it's mainly about linear system of ordinary differential equations. What we need from a linear system is just reduction to linear one and Peron approximations. And for this reason, the results on ordinary differential equations can be directly translated to the language of time scales. So what is good on this approach? It's just its simplicity that you can formulate results actually initially proved for differential equation for a wider case. What is bad here? The bad thing, which actually is a kind of challenge, is that you can vary coefficients of the system only. But in real life, you may also be interested, for example, if you are solving a system by a numerical method. So what happens if you proceed, say, from Euler method to Runge-Kutta method, or something like this, or you just proceed to non-uniform scale? So the interesting question is what happens if you vary not only this, but also the time scale. And for this question, it's open, because some ideas like shifting everything to the left may be unapplicable for this case. If you have different time scales, then you cannot use all these tricks. So this is very interesting question. If you have this kind of say non-autonomous axiom A for the case of time scale, if you can vary not only the coefficients of the system, but also the parameters of the time scale. And yeah, I guess I have a kind of 5 minutes more. Yeah, well, what else can I say? Well, there are some results on there are also some results on controllability that can be proved for time scales. Maybe I would not mention them unless it is required. I would not mention this directly. So, but there is a techniques for systems, for some systems, well, specific systems, but divergence-free systems on Euclidean space to prove their controllability. So, which means that if you have 2 points A and B, you can reach the point B from point A following delta pseudo trajectories with arbitrarily small delta. And this can also be translated into timescale language, and combined with structural stability, if you can reach any point from any point by delta pseudo trajectories, and also you have a structural stability, and you have shadowing, then you can say that you have transitivity, which can also be very very useful for some results. So let me repeat you in a nutshell what I would like to say. So we have a classical result on autonomous dynamics that axiom A and transversality stability condition implies structural stability. This result can be translated. I would not say that this is exactly the same thing, but this result can be translated to the language of non-autonomous systems. And you can speak on structural stability of non-autonomous systems of ordinary differential equations. And then you can deal with time scales, which can be treated as numerical methods. And they look like non-autonomous systems of differential equations rather than autonomous systems, because your steps may be non-uniform. And in this case, the classical results of axiom A and strong transversality conditions are not applicable. However, you can still deal with these techniques. But this work is in progress because I still don't know what happens with if we vary the time scale itself. So thank you. That's all.
Thank you very much. So, are there any questions?
Yes, there is a question about construction of the non-autonomous system related to an arbitrary system on the scale.
Yeah, let me find it.
Yes.
It should be regress. It should be. Of course, it should be. It cannot be like. It cannot be like this. So it cannot be like. So solutions.
No. Just the result itself that you can reduce. Okay. So you fix a time scale and you fix a linear system on the time scale under some assumptions on the matrix. And you can construct a system such that for T and S from the time scale, you get the same fundamental metrics.
Yes, the idea is quite simple. I just fill the gaps of the time scale. So you have. So what happens if you have a very roughly? What happens if you have a gap? So you multiply a vector by a certain matrix. Yes. So you take a product.
So the question is, one of the questions, what freedom do you have in constructing this matrix B of T?
Okay.
Do you have a large freedom in that?
Yes, I have a large freedom because actually inside the gap it can happen whatever you wish. But on the other side, you can think of this matrix as a logarithm of a certain real matrix.
Of this transition operator between
yes.
2 points of the scale.
Yes, and in this case, the only freedom is freedom to select matrix logarithm.
And if you get as you said, it's not always possible to get hyperbolic behavior for your system 8. But nevertheless, would it be possible to get reasonable conditions under which you can control the behavior of this system 8?
A very good question. I just think that in this case you should take a kind of renormalization of the time scale. If the gaps are huge, then you can kind of shrink them, and probably, very probably, this would allow you to get classical hyperbolicity.
Concerning your open problem,
But I don't know.
My question is, okay, you slightly perturb the scale. Is this system B also slightly perturbed, or do you know that?
Yeah. The good question. Well, the issue is that how you define what do you mean by slightly perturb the time scale? If you mean a small perturbation in say Hausdorff matrix on compact sets, kind of the most natural idea in this direction, then well, if say matrix A satisfies some additional conditions, like, well, for example, if we avoid this example with non-uniqueness, then you can then in general you can say that the dependence is not, but you should well, so it is true, but not always. You should think of several additional conditions. I can
Thank you very much. I don't want just now to turn this into our conversation, so maybe there are
sorry,
questions. Okay, thank you very much.
Thank you.
More questions? So no more questions. Then let us thank the speaker again.
Thank you.
Thank you.
And we have.
Thank you, Serежа. Good talk.
And we have a break till 4 p.m. Moscow time. So.
Okay. Hello, Pierre.
Hello.
You can try to share your screen now.
Exactly. I was gonna do that.
Okay.
Pierre, I'm very glad to see you.
Oh, hello, hello.
Hello. Okay. How are you?
Fine. And you?
Fine. Yes. At this
Okay.
moment, all okay. It's a good chance to see you.
Yes, I am glad to, well, almost see you, but talk a bit.
Да.
Yes.
Да, секундочку, у вас камера
Oh,
выключена.
hello, Olga.
Камера сейчас включу.
Hello, Pierre.
Ага.
Okay.
Our
thank you.
Pierre is very good.
Good.
Almost equivalence for Anosov flows. Why almost? Why not complete?
Because there is more than one another flow and 3 manifolds.
I wish you to complete equivalence.
No. There will never be equivalence.
Thank you. We are waiting your talk.
Well, thank you. I'm sorry, I'm very busy this week, so I couldn't attend other talks. But yeah.
Pierre.
Yes.
How are
Hello,
you?
Ivan.
Salut Pierre,
Ah, salut Sacha, ça va?
ça va et toi?
Oui, oui, ça va. Tu dois être très occupé.
Ah, je suis un bureaucrate. maintenant. Je ne suis pas plus un mathématicien.
Ah oui,
Presque.
presque. Bon, t'as quand même encore un peu de temps. Hello Théo. Yes.
We should wait probably still a few minutes.
Yes. One. You decide.
Okay, maybe we should start, right?
Okay.
Hello, everybody. It's my pleasure to start the next session after the lunch break. And the first speaker is Pierre Diarnois, who is going to tell us about the Anosova flows and their almost equivalence.
Thank you very much for the invitation. It's a pleasure to virtually speak in Moscow. So my talk will be about Anosova flows, and more specifically, I realized I should say three-dimensional Anosova flows because, well, I will not speak about other dimensions. So I want to discuss mostly two questions raised in 40 years ago by Fried and Gis respectively. The following two questions. The question by Fried was the following: does every transitive Another flow in dimension 3? So, well, I will come back to the definitions, but for those who know, which is probably most of you, I just asked the question in general. Does every transitive Another flow in dimension 3 admits a torus whose interior is transverse to the flow and whose boundary consists of periodic orbits? So in these questions, there are two aspects in this question. The aspect of having such a surface, which we call in general Birkhoff sections, and the fact that this Birkhoff section is a torus. So as I will explain, in this 1982 paper, Fried proved that there exist Birkhoff sections, transverse surfacing, and he asked specifically whether we can find the simplest possible, which is a torus. And this is actually still an open question, I can say. Okay, and the second question was asked by Gis a bit after that. It's connected, and I will explain in the talk how it is connected and how these two questions are now today equivalent, but it is in the statement it is not clear they are equivalent. If you take any two transitive Another flow in dimension 3, can you find a finite sequence of dense surgeries on periodic orbits that take one flow and send it on the other? So of course, when I say that, it should be explained how this dense surgery transform Another flow into Another flows, and I will speak about this quickly. Okay, so this is, and so the plan of the talk is to talk about these two questions and to give partial answers to both these questions. So the plan is the following. First, I will recall some things about three-dimensional Another flows. Then I will speak a bit, explain what are Birkhoff sections, so these transverse surfaces. Then Goodman-Fried surgeries, which is an important tool, and the corresponding notion of almost equivalences. Maybe I should have said it. If two flows are related by this finite sequence of then Goodman-Fried surgeries, we say that they are almost equivalent. Then I will explain why these two questions are equivalent, and this is actually a theorem due to Minakawa. And then I will explain why both these questions admit positive answers for algebraic flows, which will mostly be concerned geodesic flows. And then I will briefly sketch why why there should be a positive answer for all transitive Another flow. I will explain this in the end. Okay. So in an Anosov conference, maybe it's useless to recall that. But you all know that an Anosov diffeomorphism, a good example of an Anosov diffeomorphism is taking a matrix, an hyperbolic matrix, and looking at its action on the two-dimensional torus. And we say that this is an Anosov diffeomorphism. Okay, so I will just directly go to dimension 3. The first example of an Anosov flow in dimension 3 is taking the suspension of the previous example. So you take a hyperbolic matrix acting on T2. And then you take the mapping torus. And in this three manifold, which is the mapping torus, you consider the vertical vector field. So here the torus is horizontal on the picture. So if we have a horizontal torus, we take the mapping torus, and then we have the vertical direction, which gives a flow. And this flow is actually will be an example of an Anosov flow. So why is it an Anosov flow? I will give a non-standard definition, but it's close from the standard one. I will say that the flow is topologically Anosov if there exist two-dimensional foliations, so the stable foliation and the unstable foliations tangent to the flow. So here on the picture, there is the stable foliation in blue, which consists of vertical leaves, so it's the picture on the right here, and the horizontal foliation is the unstable foliations. So they have to be tangent to the flow, invariant by the flow, and we just ask that they are exponentially contracted as time goes to plus or minus infinity. So this is a topological definition, and I will and actually it's a theorem by Mario Shannon that this definition is actually equivalent to in dimension 3 to the standard definition of an Anosov flow. Well, actually, no, I'm a bit imprecise here. but okay. For me, it will be enough. Okay, a second example of an Another flow, which is also important, is the geodesic flow on a hyperbolic surface. So in general, take a surface with a Riemannian metric and consider its unit tangent bundle, which is denoted. So sigma here is a surface with the Riemannian metric, depicted here on the left. We consider its unit tangent bundle, so the set of unit tangent vectors with norm 1, and we consider on this 3 manifold, which is a circle bundle over the surface. On these 3 manifold, we consider the geodesic flow, which is just consists of, if gamma is a geodesic traveled at speed 1, then gamma of 0, gamma dot of 0 is a unit tangent vector, and the flow at time t passing through this point is just where we are at time t after following the geodesic during a time t and the direction where we are pointing. So this is the standard geodesic flow, and the theorem of Anosov is that if the surface is hyperbolic, so if the Riemannian metric is hyperbolic, then the geodesic flow is actually Anosov. And the fact that it is Anosov can be seen here in this picture on the hyperbolic plane. If we lift everything to the hyperbolic plane, here we have a geodesics, and the two-dimensional foliation, they correspond to the set of vectors that are tangent, or that are normal, so normal outward or normal inward, to a family of horocycles centered at the same point at infinity. So if we consider the origin of a geodesics here at infinity, we consider the family of horocycles centered at this point, so here in red, and we consider the family of normal vector pointing outward, these vectors. So if we travel along those geodesics backward, we all converge exponentially fast to the same point, and that's why the flow is Anosov. Here I describe the unstable manifold in red, and the stable manifold is described in blue. So this is a second example of an Anosov flow. So the question is, are there other examples of Anosov flow? So in all dimension, in dimension greater than 4, there are very few other examples. I will not discuss that. And the thing is that in dimension 3, there are other examples. And well, when in 1980, it wasn't clear, but the first example, I think, were from Handel and Thurston in 80. And then there was an example due to Goodman and Fried in 83. So actually, the construction of Goodman and Fried are different, but today we know that they more or less yield the same examples. And above this construction corresponds to making some sort of surgery. So in Handel Thurston, you make surgery along an annulus bounded by 2 periodic orbits. In Goodman-Fried surgery, you make, well, now we can say that you make a dense surgery on a periodic orbit, as I will explain in a moment. And just to say that there are other construction, and the most general I know, at least, is due to François Béguin, Christian Bonatti, and Bin Yu. It's a sort of a Lego construction because you have some basic blocks of, well, it's not another flow because these are blocks with boundary and a flow that enters by some boundary component and exit by some other boundary components. But then there is a procedure that allows gluing these blocks, and it allows you to construct a lot of another flows on 3 manifolds. And so today it's not at all clear which 3 manifolds admit another flows, whether they can admit several, how many of them can they admit infinitely many of them, etc., etc. So the classification of another flows on 3 manifolds is still something quite open. Okay, and okay, and so maybe well, one goal one can have in mind, I partially have in mind, is to, in a sense, the questions I asked at the very beginning from Fried and Gis are maybe can be seen as an attempt to put some order and to understand those numerous examples of another flows. Of course, and answering positively these questions will not solve everything, but it can be seen as a step toward understanding the set of all another flows on 3 manifolds. Okay, so I will now concentrate on this operation called Dehn-Goodman-Fried surgery. So how does that work? So assume we have an another flow. So along any orbit, periodic or not. So we have this picture. Here we have an orbit in black. We have its stable manifold in blue and its unstable manifold in red. Okay. One way of seeing this construction is to make a blow up. So we blow up this orbit. So we replace every point by the set of normal directions. And so on this, on this blown up torus, we have still the flow extends here, and the flow is still in the same direction, but there is also a small normal tangent direction. So the stable manifold, they yield just periodic orbits on the boundary of this new three manifold. So now we have a three manifold with boundary. The boundary is a two-dimensional torus. On this two-dimensional torus here, we have 4 periodic orbits corresponding to the stable and unstable directions. Well, 4 or 2, depending whether the manifolds here are orientable or not. But let's say 4 for simplicity. Okay. And now what we do is that we consider a curve on this torus, which will be another curve. So not a meridian. It will be a curve here in green, which will be transverse to the flow, but not necessarily a meridian. So here, for example, I draw the curve that travels once along the longitude and then 3 times along, twice along the meridian directions. Okay, and what we will do is now to blow down this new green curve, exactly as in a dent surgery. And the thing is that, so when we blow down this curve, of course, we don't have anymore a flow. I mean, we have a flow on the complement of the torus, but here it's not clear that we have a flow. But what we keep is a one-dimensional foliation, and we can reparameterize this one-dimensional foliation in order to get a flow. And this is the theorem of Shannon, that actually there is a way of reparameterization that this one foliation is actually Anosov, topologically Anosov, and so Anosov. Okay, so this is the operation. So basically, topologically, there is nothing more than a dent surgery on the periodic orbit. And on the dynamical side, you have to take care in order to define properly a new Anosov flow, but this can be done. Okay. So the thing is that after you do that, you see that if when you blow down just a meridian circle on this picture, on the center picture, you get back transversally. What you get back is still 2 invariant foliations. Here, what happens is that the green curve I picked here intersects more than twice actually the stable leaves and the unstable leaves. So when we blow down, the 2 foliations we see transversally, they are not anymore like nice foliations, but they are singular foliations. So here we have a green curve that wins more than once along the meridian directions. The picture we see transversally along a small transverse surface is not anymore a nice Anosov picture, but it's a pseudo Anosov picture. But if the green curve I choose is actually it cuts the stable or unstable direction only twice each, we get a 1 foliation, which is an Anosov foliation. So what it means is that if we make an integral surgery, integral in the sense of in the topological sense, so which means dent surgery with integral coefficients, then we get an Anosov flow. Okay. Okay, so this is the Day-Goodman-Fried surgery. Now I want to go toward the Fried theorem concerning the existence of Birkhoff section. So before defining a Birkhoff section, I will just say one elementary, well, not so elementary thing, but one other thing on Anosov flows, which is also an old theorem due to Ratner, which is the existence of Markov partition. So, well, probably you all know what a Markov partition is, but here is an example. If we take the matrix 2, 1, 1, 1 acting on the torus, we can cut the torus along rectangles bounded by stable and unstable leaves. Here, there is a way to cut the torus into 5 rectangles, A, B, C, D, E, so that if we look at the image of each rectangle by the map, here the map A, so here, for example, the rectangle A is in green, it is stretched along the unstable direction and contracting along the stable direction. And so it turns out that the rectangle A is sent on another rectangle here, which travels through A, C, and D. The point being that the stable borders of the image of this rectangle, so the small vertical sides here, they are included inside the vertical sides of the partition. So A, B, C, D, E is called a partition. So this decomposition into 5 rectangles is called the partition. And the point is that if you take the image of a rectangle, its small size are included into the vertical, the stable sides of the partition. And conversely, if you go backwards, so if you take the pre-image of A by A inverse, so by the matrix inverse, then this side, the unstable side will be signed inside unstable side of other rectangles. And so, well, this Markov partition, when they yield a certain transition matrix, which just tells you where the image of each, well, for each rectangle, its image will intersect some other rectangles, and you make the list of what they intersect. And then, given this transition matrix, we can define a set of admissible words. So what it means is that you consider bi-infinite sequences in terms of these 5 rectangles. So bi-infinite words in the letters A, B, C, D, E. And then a word is admissible if the two syllables, if the syllables made of 2 consecutive letters belong to this transition matrix. So basically, it says that after A, you can only go in A, C, and D, for example. And after B, the same. After C, the same. After D, you can only go in B and E, and so on. And so it tells you, okay, so this defines a set of admissible words. And the main point of a Markov partition is that there is a semi-conjugacy between the dynamics on the map on the torus and the dynamics just given by the shift on this set of admissible words. Say differently, you can describe all the orbits of the map 2111 acting on the torus as just the set of bi-infinite admissible words on this alphabet. In particular, if you want to understand the periodic orbits of this map, it just corresponds to the admissible periodic words in this language. So just the semi-conjugacy comes from the fact that then you have the borders of the rectangles. So there is a bit more orbits in this shift map that's in the torus, but really few more. Okay, and the theorem of Ratner from 1968 is that if you have a transitive Anosov flow in dimension 3, then it admits a finite Markov partition. So for a flow, a Markov partition is not exactly the same thing. It's a family of rectangles here, or maybe say differently, it's a family of flow boxes. And since we have an hyperbolic flow, an Anosov flow, the flow boxes, they will be contracting in one direction and expanding in another direction. So a flow box looks like that. So that if you look at how the entrance and the exit side of your flow boxes match, well, it will turn out that the entrance side will be completely covered by rectangles that go from one side to the other side, and the same for the exit side. So there is the same kind of compatibility condition, which allows you to encode all the orbits of your flow by just the intersection with the collection of boxes you travel. So this is how this is a Markov partition for an Anosov flow. Okay, and the main tool I want to introduce, to use, is the notion of section. So just quickly, a global section for a flow is a compact surface. So we are back in a global context of just an arbitrary flow here. So if M is a 3-manifold and phi a flow, a compact surface S with no boundary, which is embedded in the 3-manifold, transverse to the vector field, and it cuts all orbits with it bound in time. This is what we call a global section. And when we have a global section in a general dynamical system, we are quite happy because then we get a first return map on this Birkhoff section, on this global section, sorry. So starting from a point, you just follow the flow and you hit another point of the surface. And so up to reparametrization, your dynamic here, M phi, is just the same as the suspension of some of the first return map. So this is a very nice tool, a global section. Unfortunately, Anosova flow do not admit global section, but what they admit, as I will explain, is a Birkhoff section. A Birkhoff section is almost the same thing as a global section, except that it's a surface with boundary. So here the Birkhoff section is a surface in the three manifold with, on the picture here, two boundary components, such that the interior of the surface here is embedded in the surface and transverse to the vector field. So exactly as before. And just the boundary of the surface is a finite collection of periodic orbits. And we ask the same thing, that every orbit cuts the surface in positive and negative time. So if you start from any point, for example, here on the picture, you flow forward or backward, you hit the system within bounded, the surface within bounded time. And when we have this, we have almost the same advantage, because up to removing the boundary, well, two things can be said, up to removing the boundary of the surface. So if we only consider what happens on the interior of the surface, we still have a first return map. And so we can consider the suspension flow of this first return map. And so our flow away from the boundary of the Birkhoff section is just a suspension flow. And actually what we obtain is what topologists called an open book decomposition of the three manifold. An open book decomposition is exactly this. It's a decomposition of the three manifold as what is called a binding. So here, which is the set of periodic orbits that are in the boundary, and a family of surfaces that fill the three manifold and around the boundary look like the pages of an open book. Well, this is just to say that from a topological point of view, this is something nice. And from a dynamical point of view, you have a first return map. So you can study the dynamics through the first return map if you wish. Okay. One additional remark is that then, as I said, if you remove the boundary, you have a suspension. But then what you can do also is to make a Goodman-Fried surgery on the boundary with the right slope that will then transform the boundary, that will kill the boundary, so that actually that will replace the boundary with just with something contractible. And so what happens is that away from the boundary, we had a suspension flow. But if we make the right surgery on the boundary, now we even have a suspension flow on a closed surface. So on the closure of the surface S, we may consider we have here a first return map. And so, okay. So what this means is that when we have a Birkhoff section, then up to a surgery on the boundary, we also have a suspension which is almost as nice. Okay. And so just the definition from the title of the talk, maybe I should have given it before, but then we will say that two flows are almost equivalent if there exists some periodic orbits, here gamma 1, gamma n, of the flow, and some coefficients that here I chose rational, but well, actually in most cases they will turn out to be integral, such that if you make a surgery, if you start from the first flow and you make surgery on the periodic orbits with the given slopes, then you obtain the new slope. We say that two flows are almost equivalent. And okay. And so when we have a Birkhoff section, we can say that the flow is almost equivalent to a suspension flow. This is the main point. Okay, so just a few, well, yes, quickly some examples of Birkhoff section. Well, just here, I will not use the formula. If you consider the Hopf flow on S3, so the Hopf flow is the flow whose periodic orbits are big circles on S3. So if you consider one periodic orbit here in orange, you can consider the disk bounded by this periodic orbit. And since you know that all orbits of the Hopf vector field link once, you know that all orbits which will intersect this orange disk. And so here you find a Birkhoff section, which is just a disk. And actually, if you follow one circle, you come back at the same point after one turn. So the first return map is just the identity. So it's the simplest example of a Birkhoff section, which implies that actually the S3 equipped with this Hopf flow is almost equivalent with the definition which I gave to just the trivial flow on D2 cross S1. So if you take the solid torus, well, and with the trivial flow that follows the circles, then it is almost equivalent to the Hopf vector field. Okay, another example, which is maybe the oldest, one of the oldest example of a Birkhoff section, is consider a sphere with positive curvature. Here on the picture, I try to draw a sphere with positive curvature. Then you know it actually goes back to Poincaré, I guess, that there is a simple periodic geodesics that separates the closed geodesics that separates the sphere into two hemispheres. And then you take the set of tangent vectors pointing into one of the two hemispheres. So this is a surface in the unit tangent bundle. And you can see that it's actually a circle corresponding to the red curve cross an interval corresponding to the interval of direction that we choose. So it's an annulus. And this annulus is a Birkhoff section for the geodesic flow. So it's a second example. And maybe a third example, which is due to Fried, is if you take the geodesic flow on a hyperbolic surface. So if you take the geodesic flow on a hyperbolic surface, you can start with the same idea. So you take some periodic geodesics here, and then you lift it in the unit tangent bundle. So the geodesics lift the geodesics. Well, a geodesic naturally is unoriented, but you can orient it in two directions. You can go here on the picture from left to right, and then you obtain the blue geodesics, or from right to left, and then you obtain the orange geodesics. So what I mean is that a geodesics lift as two orbits of the geodesic flow in the unit tangent bundle. And now you do the same. You choose one side of this geodesic, and you take the set of tangent vectors pointing in that side of the geodesic. So here we take on the picture, we take the set of geodesic pointing in the back. So this gives a set locally. This gives in the fibers of the geodesic. This gives a rectangle, a ribbon. Okay, and you can try to extend this ribbon as much as you can. And the thing is that if you just take one ribbon, either it is simple and then it will not be a Birkhoff section because it will not intersect all orbits, or you can take a collection of ribbons. So what Birkhoff proposed and was rediscovered by Fried is that, for example, on the genus 2 surface, if you take this collection of geodesics, so this consists of 6 geodesics, here 6 simple geodesics. These 6 simple geodesics, they decompose the surface into 4 hexagons, and then you take the set of tangent vectors pointing toward 2 of these 4 hexagons, and this gives a surface in the unit tangent bundle. So the thing is that above every point in the here generic point on the geodesic, we obtain a rectangle as before. Now, if we look at the double point, the picture is a bit more complicated. It is depicted on the right. So if you take a double point, an intersection point of our geodesics, then we have locally 4 rectangles that arrive in the unit tangent bundle, and these rectangles, they glue correctly and to yield a surface, and this surface is transverse to the geodesic flow, and you can check that it intersects all periodic orbits, so it's a Birkhoff section. And actually, you can even, well, combinatorially, you can compute the Euler characteristic of this surface, and you check that this surface here is a torus. Okay, and okay, and so you have a first return map on this torus, which in general is pseudo-Anosov. It's pseudo-Anosov because along the boundary orbit, you control a bit less what happens, and so we have a torus with some boundary components, actually 12 boundary components corresponding to the 12 oriented geodesics in the boundary here. So we have 12 boundary components. Along these boundary components, the flow is only pseudo-Anosov. But it turns out that if we blow down these boundary orbits, and in this particular situation, we obtain actually an Anosov map. So the first return map will be an Anosov map on the torus, and it can even be computed in this example on the genus 2 surface. It's this map of the 2-dimensional torus, which implies that the geodesic flow on a genus 2 surface is almost equivalent to the suspension flow of this hyperbolic matrix. So this construction of Birkhoff-Fried shows you that if you an Anosov flow which has no special connection with the torus actually here contains a torus which is a Birkhoff section, and so the first return map is just an Anosov map of the torus. Yes, and so now I come back to Fried theorem. What Fried proved in 1982 in his thesis, more or less, or just after his thesis, is that if you take an arbitrary transitive Another flow in dimension 3, it admits such a Birkhoff section. So in the previous example, it was a Birkhoff section which was a torus, but in the general case, you have a Birkhoff section. And so as a corollary, it is almost equivalent to the suspension of some pseudo-Another homeomorphism of some surface. And so the question he asked was, can we find a Birkhoff section which is a torus, in which case the corollary would be that it is almost equivalent to the suspension of some Another homeomorphism of the torus. Yes. Okay, so this is a Fried question that I recall, and I recall also this question, which can be stated a bit differently. Are all transitive Another flow pairwise almost equivalent? Okay, and now I will explain why these questions are now the same. And the answer is given by a theorem that was stated by Minakawa around 2013. Minakawa never published a proof. I don't know why, but it was stated, and there was a video of a talk where he explained this, and there was also an abstract of a talk where the scheme of the proof was explained. So what I will explain quickly is the theorem of Minakawa. The theorem of Minakawa, which was really a surprise for me, is that if you take a matrix in SL2 of Z, so take an Another diffeomorphism of the torus here with orientable foliations. And actually, the suspension flow of an Another diffeomorphism of the torus is almost equivalent to the suspension flow of the matrix 2111, the so-called cat map. So what the theorem says is that you take an arbitrary suspension of a matrix. Somewhere in this suspension, there is a Birkhoff section, which is also a torus, but with boundary components. So the boundary consists of periodic orbits. And the first return map is given by this matrix 2111. And the corollary of this theorem is that if you admit a genus 1 Birkhoff section, so then the first return map will be something of the form, will be a certain matrix A. Then using the theorem of Minakawa, you know that there is another Birkhoff section whose first return map is 2111. And then it turns out that as soon as you admit a genus 1 Birkhoff section, then actually you are almost equivalent to the suspension of 2111. And so this relation is transitive, so it's an equivalence relation. So which means that as soon as you have a genus 1 Birkhoff section, then you are almost equivalent to 2111, to the suspension of 2111. Okay, and so the second result I want to highlight is the following theorem that we proved with Mario Shannon in 2019. Is that now if you take a hyperbolic 2 orbifold, so I spoke about hyperbolic surfaces. Here we consider a more general case of a hyperbolic orbifold, which means it's a hyperbolic surface with some cone points. So there are points where the surface is singular, so that the total angle around this point is not 2 pi, but it's 2 pi divided by q for some integer q. So it's not anymore a surface, it's called an orbifold, but the thing is that then it has a well-defined unit tangent bundle, which is a 3-manifold, and this unit tangent bundle is equipped with an Another flow. Another way of saying that is that you consider all sorts of quotients H2 mod out by a Fuchsian groups, and in this way, considering the unit tangent bundle to H2 and modding out by the Fuchsian groups, you obtain a 3-manifold with a certain Another flow. Okay, so you have a more general notion of, well, so for this definition notion of hyperbolic 2 orbifold, you have a geodesic flow, and all these geodesic flows, they emit genus 1 Birkhoff section. And so using the above corollary, they are all almost equivalent. Okay, so in the last 10 minutes, I will try to explain the tools used for both this theorem. Actually, there are some common ideas in these proofs. And I will explain, I will mostly explain the proof of Minakawa's theorem, and I will explain our theorem with Shannon with just one picture or two. And the main tool which is really useful was introduced actually by Fried is the following, what I like to call the Fried sum of two transverse surfaces. So if you take two surfaces, S1, S2, transverse to a certain vector field. So X is a vector field on a 3-manifold. S1, S2 are two surfaces with boundary transverse to this vector field. So think of Birkhoff section. And then you define the Fried sum as just the union of these surfaces. Okay, but the union, they may intersect. So the union is not a nice embedded surfaces. So you take the union and you desingularize the intersections transversally to the flow. So what will happen in general is that, well, first, what I should have said first is that first you perturb them to make them in generic position, one with respect to the other. Since they were transverse to the vector field away from the boundary, you can perturb them away from the boundary to make them transverse. And then they will intersect along one-dimensional submanifolds, which will look like this. And so what you do is that transversally, you see that you have a flow direction. And so you will reconnect the different piece of the surfaces in such a way that you remove this intersection. Okay. So homologically, you don't change, it's just the sum in homology, but just for the surface itself, it's not anymore the same surface. So I said you do that. Of course, on the boundary, you have to be a bit more careful. So on the boundary, you will do this operation up to the boundary where here things just live in the same at the same point. Okay, I am a bit sloppy about what you do on the boundary, but you can do it on the boundary at the expense of maybe perturbing a bit. And then you obtain what we call the Fried sum. And John, one important remark is that under this operation, the Euler characteristic is almost additive. It's not exactly additive. What is additive is that if you consider your surfaces and you remove from these surfaces the boundary of both surfaces. So this is maybe the thing that perturbs. So imagine that here, for example, on the right picture, the orbit that is drawn, the boundary orbit here is in the boundary of S1, the black surface, but not of S2, the orange surface. But still, you will remove from S1, so from the orange disk here, from S2, from the orange disk, you will remove a point on this here, just to remember, I mean, just to compute the characteristics. And if you do that, so if you remove enough points and enough boundary components, then the Euler characteristic becomes additive under this operation, which will be very convenient to control what happens when we use this operation. Okay. Okay, sorry, I will just skip this part. I just wanted to explain quickly the proof of Fried that every Anosova flow admits a Birkhoff section, but this is well, I will just keep that. So Fried proved that yes. Okay. Now I want to explain Minakawa's theorem. The proof of Minakawa still owns a lot to Fried's proof that I just skipped, but I will try to explain it right now on this on an example. So the thing, how does Minakawa work? You start from an arbitrary matrix, which is not 2, 1, 1, 1, because for 2, 1, 1, 1 there is nothing to do. So you start with a matrix which has trace strictly larger than 3. If it has trace strictly larger than 3, for example, on this picture, the trace is 14. On this picture, so it has trace -2 fixed points, so it has 12 fixed points. So this is a map on an Anosova map of the torus with 12 fixed points. It turns out that if you look at all the segments connecting the fixed points, you are able to find here a segment starting from one fixed point here on the top left corner, connected to another fixed point, so that if you apply the map A to this segment, it is mapped of 6, both extremities are fixed points. It's a new segment connecting these fixed points. But it turns out that you can find the starting segment so that the union of both these segments it's just a simple closed curve on the torus. Say. So here you see that the main point is that the image of the segment does not intersect the segment away from its endpoints. So you can do that, and since the fixed points for a map on the torus form a lattice, if you have one segment like this, you can also translate it, and you have another segment like this, starting just opposite, or say you just act by a symmetry around this point, 180-degree rotation around this point, and then you find another segment. So you find two segments here, these two segments that are sent on two other segments, and so together they draw a certain rectangle on the torus. Yes, they draw a certain rectangle on the torus. So here is another view of the same rectangle on the torus, just using a translation from vector 1/2, 1/2. So it's the same vector. Okay. Now, if we consider the suspension flow, what will we have? If we consider the suspension flow, we can still consider this rectangle. And so if we take one of these segments, if we push it along the flow, so we push it along the flow, we obtain another segment that comes back after the suspension and glue to the other segment. So what I want to say is that, yeah, maybe I should have drawn this picture. Yeah, sorry, I still show you this picture which shows the idea. Sorry. So here we have roughly the same picture with less points drawn. We have this purple segment here, which is sent on the green segment, and another purple segment sent on the green segment. And so if we take the suspension of this picture, if we take the suspension of the purple segment, they will describe in the three manifold a certain band that will glue back, say change color slowly and glue back to the green segments. And so the union of this rectangle here in orange with these two bands will give a certain surface, which is actually a pair of bands. And you can smooth this surface to make it transverse to the flow. So this is how you obtain a certain pair of bands, which is transverse to the flow and whose boundary consists of the suspension of these points here. So if I go back to what I was explaining to Minakawa's proof, here, starting with this green rectangle, I take the suspension of its sides and I obtain a certain surface, a pair of bands embedded in the three manifold, whose boundary is in the suspension of these three periodic points, so these three periodic orbits. And so this pair of bands is embedded in the three manifold. And now what we do is that we take the freed sum of this pair of bands with a horizontal torus, which was a section before. And if we make the correct computation of the Euler characteristic of this freed sum, well, we find -4, but it actually has 4 boundary components. And so what we understand is that actually we have a new Birkhoff section, which is still a torus, but it's a torus so that the first return map has actually less fixed points than before. The reason for that is that the range points that were inside the rectangle for the new Birkhoff section, they are not anymore fixed points, they are periodic points of order 2. So the number of fixed points has decreased. This means that the first return map is an Anosova map with less fixed points, so the trace is smaller and decreases. So starting from a matrix with high trace, you decrease the trace step by step until you reach, say, trace 3, and you are almost equivalent. So this is the proof of Minakawa's theorem. Actually, you can control a bit more what happens the first return map, but I will not explain this. Okay, and I will just finish. So this proves Minakawa's theorem. I will just finish with some pictures that every hyperbolic 2 orbifold admits a genus 1 Birkhoff section. So I already explained the picture. If there is no singularity, so it's actually your orbifold is a surface. Now, well, some pictures, some other cases can be understood quite elementary. For example, if you take now an orbifold that is a sphere, so genus 0 orbifold, but with 3 conic points. So this is a picture you may have already seen, the tiling of the hyperbolic planes with some triangles with order pi over p, pi over q, pi over r. So this gives pictures like that, hyperbolic pictures like that. And here you can describe some surfaces which lives in the unit tangent bundle. So here it's a bit similar, the idea that you take this sort of foliation. So here this triangle is actually the ortic triangle of this hyperbolic triangle of this hyperbolic orbifold, which meaning it's a closed geodesics here bouncing like this. Then you foliate the interior of this closed geodesic by sort of butterfly-like foliation, and you take the union of the tangent vectors to this thing. And then you compute And then you understand that this thing has actually Euler characteristic -1 and one boundary component. So it's a surface transverse to the geodesic flow, which is a torus. And then if you take an arbitrary hyperbolic orbifold, you can mix all these ideas. And so, well, you can find a certain collection of geodesic, which is here in green and blue. So the green part mimics what happens on the surface, and the blue part mimics more or less what happens on this genus 0 orbifold. Okay, so this defines a certain collection of closed geodesics of this geodesic flow. And then here you can find a surface bounded by the lifts of these geodesics in the unit tangent bundle. It is described here. So on the green part, it looks a bit like what I explained on the surface. In the blue part, it looks a bit to what I just explained. And you compute and you see that it has genus 1. And so every geodesic flow admits a genus 1 Birkhoff section. And I just finish with stating one theorem, which I am currently writing, but it's taking time. So I already announced it in other conferences 1 year ago, that if you have a transitive Anosov flow, so it's just for generalizing. Now, if you think about the general Anosov flow, you know it has a Birkhoff section, but you don't know the genus. So the strategy we could imagine is start from a Birkhoff section with genus G and try to find another simpler Birkhoff section with less genus. And so this theorem is a first step in this direction. If you have a transitive Anosov flow with an additional assumption that it has orientable foliations, and it has a genus 2 Birkhoff section, and I have a restriction on the first return map. So if you have a pseudo Anosov homeomorphism with orientable foliation on the genus 2 surface, it can live in two so-called strata, which are called H2 and H11. So here I treat only half of the cases. If the first return map is in H2, then actually you can find, using IDs borrowed from Minakawa, you can find a genus 1 Birkhoff section. Okay, so I will just stop here. Thank you.
Pierre, thank you very much for your nice talk and beautiful pictures. So any questions, please, comments?
Can you explain what precisely, more precisely, what is the strata H2?
Yes, it's when you look at the you look at the foliations, the invariant foliation of your pseudo Anosov map, then they have some singularities. And H2 just means that there is just one singularity with total angle 6 pi, and H11 means that there are two singularities with angle 4 pi each.
Okay.
Yes. So yes. So actually, I say I treat half of the cases. H2 is in a sense much smaller than the other one, so it's less than half of the cases.
Any other questions? Okay. If not, let's thank the speaker again. And we meet again in 12 minutes for the next talk. Time for prepare for 10.
Thank you. Bye. Stop.
Pierre, tu m'entends?
Oui, je t'entends, Christian.
Tout à l'heure, j'ai essayé de poser une question, mais je n'avais pas de micro. Maybe I speak English. So you spoke about the existence of Markov partition in the transitive case. Do you have any either idea about existence or the contrary counterexample?
For non-transitive?
For non-transitive.
Well, I don't know. François Béguin knows has said things about
no,
this.
It was about Birkhoff section. You don't have Birkhoff section if you have no.
Yeah, exactly.
About Markov partition. I guess we can ask to François, but.
Yeah. No, that's right. I was mixing. No, well, I have no idea, but that's a good question.
Because you know the result by Shannon about topologically Anosov flow assume the existence of Birkhoff section, so assume the transitivity of the flow, but maybe we could bypass that if we knew that there was always Markov partition. So it could be maybe possible to extend.
Yeah, that's a nice question. Okay, I always forget the proof of this existence. I mean, I remember the scheme, and then I go into Hafner and Sinai's paper, which are quite hard to read for me. But well,
because
I mean, you know, the strategy is you start from some finite number of periodic orbits,
yes,
and then you launch the stable and unstable manifolds, and if you are lucky,
yes. But with that, you can build Markov partition for the attractors, for the repeller, for the saddle pieces.
Exactly.
But we will need compatibility between them. So
exactly. That's why, I mean, that's why in the transitive case it works, and in the non-transitive case, well, then I don't know what we get. But I mean, yeah, we only obtain things for the attractors and repellers like that.
Okay. Thank you.
Well, you're welcome.
Do you see my screen properly? Okay.
Yes, we do.
Okay, guys, so let's start our next talk. And the next speaker is Theo Marty, who will speak about Birkhoff sections and orbit spaces of Anosova flows.
Okay, so thank you for the invitation. I'm really happy to discuss what I've done during the conference. So what I will explain is in the same spirit that what Pierre Dornois explained in the last talk. So that is understanding Anosova flow up to some kind of surgery. So yeah, maybe I will represent just the thing. So one question is to understand Anosova flow up to some fluid surgery, which I will maybe will give with definition. And so I want to present a relation between two notions, so Birkhoff section, which represented in the last talk, and orbit space. So I will explain all of this later. So I want to explain some kind of topological relation between these two objects. So just to remind, an Anosova flow is a globally hyperbolic flow. So you can have in mind the picture that Pierre drawn during the last talk. So close to an orbit, you have two foliation transverse to the flow. No, two foliation which are transverse and which contain the direction of the flow. One which is expanded, one which is contracted, and both are preserved by the flow. So, so just for some notation, I will write M on a closed three manifold. Later, I will require that the manifold is oriented, but for now, just a closed manifold. Phi will be an Anosova flow. And I will denote by, so those two interesting foliation that I will use are the stable foliation, the unstable foliation and the stable foliation. So the stable foliation is contracted by the flow, the unstable is expanded or contracted in the past. So yeah, the question is to understand the set of Anosova flow for three manifold up to fluid surgeries. So just to recall fluid surgeries, so it was well defined in the previous talk, but fluid surgeries, it's a surgery along a dense surgery. It's a dense surgery along a closed orbit. So this is a question, and understand what are the set of this flow. And that's operation. And the two notions that I want to relate are the orbit space and the Birkhoff section. So Birkhoff section were introduced in the previous talk, but I will really give the definition. Orbit space was not present. So just briefly, these two kind of objects are two topological notions which capture some topological property of the flow, to topological property which are transverse to the flow. So, and we'll explain some relation. Mainly, the relation that I will want to explain is that under some hypothesis on the existence of some kind of Birkhoff section, the orbit space, which I will introduce, has some nice topology. So what is the orbit space? The idea of the orbit space is to consider the set of orbits, but in a nice way, so it can be used later. So I take the data that I've wrote before, so the three manifold, an Anosova flow, and the two main foliation. So yeah, I'm only interested in the weak stable and weak unstable foliation, so in case it matters. So the two main weak foliation, stable and unstable. I consider the universal cover of the manifold M, so M tilde, the universal cover. On this manifold, I can lift the Anosova flow and the two stable and unstable foliation. So for example, if I have a closed orbit inside M, in the universal cover, the orbit will, the lift of that orbit will not be closed. So you will have an orbit homeomorphic to R, and then I lift everything back. So at that step, I just lift everything to the universal cover, and then we quotient the universal cover by the flow. So you contract every orbit of the new flow in the universal cover to one point. So you obtain here a topological space. And the two foliation on the universal cover, since they are invariant by the flow, the image are also two foliation, also foliation in that space. So I will give later what is that space. But here you have two foliation, two stable and unstable foliation coming from the foliation of the flow. So the first interesting property is that this space is a plane. So it has been proven by Fenley and Barbo. So it's a topological space plane. So you can have in mind that you on the universal cover you have this kind of picture. So transverse to one orbit, you have the stable and unstable foliation. And when you conjugate everything, this orbit become one point. Its stable foliation become one curve, and its unstable leaf become transverse curves. And so on the orbit space, you have a plane, topological plane, plus two transverse foliations, which characterize somehow some topological property on the flow. So the orbit space plus the two foliation can have many shapes, many forms. There is one particular case which are interesting. So three particular cases. There is one property called R cover that we'll explain, which are the case that interest me the most for that talk. So what is the case R covered? We look at one of the foliation, for example, the stable foliation on that orbit space. If you consider the set of leaves of that orbit space, you obtain a topological space. And the interesting case when it's R, when it's Hausdorff, so when it's homeomorphic to R. In that case, we say that the flow is R covered. So here I said the set of leaves of the stable foliation, but it's equivalent if you consider a set of unstable leaves. So it's equivalent to have the set of leaves of the stable foliation homeomorphic to R of the set of unstable leaves. And in that case, there is many things that we can say that this kind of flow have been studied by Fenley and Barbo, and there are things that we can say. So the first thing we can say is that the flow is transitive, and that the shape of the orbit space have some particular kind of. There is three cases for the orbit space. So if you consider the orbit space plus the two main foliation, there is three cases which are given. So I've written here, but I will draw some picture. So the first case is the trivial orbit space, which is given by R2 bifoliated vertically and horizontally. In that case, it has been proven that by Solodov, that this case is equivalent to suspension. That is, an Anosov flow admits that kind of orbit space if and only if it is topologically equivalent to suspension. There is a homeomorphism to the suspension on a torus of maybe the suspension of an Anosov diffeomorphism. Anosov So if a flow admits that kind of orbit space, there is a homomorphism from the manifold to the suspension manifold, which sends the orbit of the first flow to the orbit of the suspension flow. Okay, the second case for the orbit space possible when the flow is air-covered is given by a diagonal strip. Like that. So the orbit space is given as like the second diagonal or diagonal strip, and the two foliation, stable and unstable, are given by the vertical and horizontal foliation. And we'll come back to that case. The last case is when the orbit space is given by the other diagonal strip, with also the vertical and horizontal foliation. So these two cases are the ones that I will speak about in my talk. They are called skewed. So this one, the second case is called positively skewed. The third one is called negatively skewed. So this kind of topological space correspond, in fact, this one corresponds to the geodesic flow on a hyperbolic surface. I mean, correspond means the geodesic flow on a hyperbolic surface is an example of such a orbit space. Okay, so with one more thing I want to say. So apparently, I mean, not apparently, you can see that these two cases seems to be equivalent. So there is a homomorphism from one orbit space to the other, which send the horizontal foliation to the horizontal foliation and the vertical foliation to the vertical foliation. So there is a reason that we distinguish these two kind of orbit space. The reason is that when we have a skewed air-covered flow, so for one of these two cases, the manifold, the ambient manifold, M is orientable. Here, in that case, M is orientable. And these two cases correspond to the two orientations on the manifold M. So to be more precise, if I fix one orientation on the manifold M, this orientation somehow can induce an orientation on the orbit space. So for example, you have an orientation on M, you lift it to an orientation on the universal cover. Then when you project to the orbit space, you can fix one orientation on the orbit space such that locally this orientation plus the direction of the flow induce orientation on the universal cover. And when you add this orientation, these two cases are different. So for the rest of my talk, it's relevant to take an oriented manifold. So I fix an orientation, and these two type of orbits flow will be different. Okay, so I will let the orbit space for now for a few minutes. I will reintroduce the Birkhoff section and other type of transverse surface which interests me. Then later I will explain some relation between what I presented on the orbit space and what I will present on Birkhoff section. So Pierre explained in the previous talk what is a Birkhoff section. I want to give first a different notion, a more flexible notion of surface. It's called a partial section. So its partial section is a similar kind of surface which is immersed in the manifold. We suppose that the interior is transverse to the flow and that the boundary of the surface is a union of closed orbits. So similarly to Birkhoff section, but we don't ask anything on the intersection with the set of orbits of the flow. Just a topological surface which behave well with the flow. And the particular case which are a bit more interesting when it's a Birkhoff section. So it's a Birkhoff section when intersects additionally to the two initial property, when it intersects every orbit in bounded time. So Birkhoff section are useful when you want to deduce some dynamical property of the flow. Partial section, I believe, are a little bit less useful for the dynamic because you miss the information for most of the orbits, but they are still interesting when you want to capture some topological property on the manifold and for the flow. So yeah, I will just draw two pictures for the partial section and Birkhoff section. So when you consider an orbit of the flow, more precisely a boundary component of a Birkhoff section or a partial section, locally it can look like that. That is, that boundary here is an orbit of the flow. And if I denote S a Birkhoff section, it's also a part of the boundary of the Birkhoff section or the partial section. Outside the boundary components, the flow is transverse to the surface. So somehow the surface turns around the boundary component. So you can also have like the symmetrical picture. Here, so the boundary of a Birkhoff section can also look like that around the surface. So if in general it does not make sense to like draw something turning around in a three manifold, and since we have a Birkhoff section, we can draw a stable leaf. For example, here it's a stable leaf. And you can compare how the surface turns around the boundary relatively to that stable leaf. So when you fix that stable leaf and the framing it's induced on the orbits, it makes sense to draw like a surface turning around the orbits. So these are the two pictures for Birkhoff section, or the two simplest pictures for Birkhoff section along a boundary components. I'm saying simplest because you can have multiplicity. You can have several copies of this kind of picture which are glued to that boundary. For a partial section, there is another behavior which is possible. So I will draw it on the side. So for partial section, you can have some kind of surface which somehow turn around the boundary components, but does not do any turnaround. It's like it just slightly turn around. It's slightly turn around the boundary component just enough so that when you do one turn around the boundary, the closed orbit, you have compensates the action of the flow. So I mean that this segments should be identified with the one on the bottom one by the flow. So you can also have the similar picture on the other side. And let me draw quickly how the flow acts. So the flow should go like that. In particular, so in red it's a stable foliation, in blue it's an unstable foliation. Okay, so maybe for now it doesn't make sense why I draw this picture. I draw this picture because I want to capture some behavior on the boundary of a Birkhoff section or a partial section, and this behavior will be decided by this kind of picture. So yeah, thanks to Fried, we know that Birkhoff section exists when the Another flow is transitive. So the construction of this kind of Birkhoff section, it allows you to construct a lot of Birkhoff section, but you don't control a lot of things on this Birkhoff section. The genus can be really high. The boundary of this Birkhoff section are not very nice. So I will discuss something which is really a bit thinner. So what I want to discuss, the additional thing I want to add on the boundary of a Birkhoff section is a sign. So I want to add a sign. I'll come back to this picture in a minute. So I suppose now that manifold M is oriented. So otherwise, I can't do what I will explain. Then I want to distinguish these two kinds of behavior for the partial section. And I will distinguish them by saying that this one is a positive boundary component. I will explain more precisely what it means. And this one is a negative boundary component. So more precisely, since you have an orientation on the manifold and the surface is transverse, you can induce an orientation on the interior of the surface. And this orientation, you can put it, you can also induce an orientation on the boundary component. So it's just a topological construction. So since the manifold is oriented, when you have a Birkhoff section or even a partial section, you can orient the boundary component of the partial section using the orientation of the manifold. But since the flow, our boundary component is also an orbit of the flow, there is another orientation which is given by the flow. So when these two orientation match, the boundary component will be set positive, and when the two boundary component does not match, it will be a negative boundary component. So when I just come back here to explain the difference between these two pictures. So here you have on the left, you have a negative boundary component. On the right, you have a positive boundary component. And you can relate this with the linking number of the surface with the stable foliation. So you have a linking number which is non-zero, and the sign somehow gives you the sign of the boundary component. When you are on the right picture, the linking number is 0, so you can't decide using the linking number if it's a positive boundary component or a negative boundary component. But the sign will depend on which quadrant is the surface. So here you have a quadrant which is determined by, which is bounded by a piece of stable leaf and a piece of unstable leaf. for example, for this gradient, so it will correspond to some sign. And so for this gradient, it's a positive boundary component. And for this gradient, it's a negative boundary component. So the one I draw on the back is a negative boundary component. So as you can see, the sign depends on which boundary component is immersed on the orbit. So if a partial section have both these two kind of a picture around the same orbits, it can have two signs along the same orbit, but the sign is really not on the orbit, but on the which boundary component of the surface is immersed on the orbit. Okay, the surface which are particularly interesting for me are the surface, the partial section and the Birkhoff section, which have a non-empty boundary. So say here, non-empty boundary, and whose all boundary components have the same sign. For example, section is set positive if all its boundary components are positive. Okay, and the theorem I want to explain is that in that setup, so given an Anosova flow on an oriented three manifold, the flow is air covered and positively twisted if only if it admits a Birkhoff section, a positive Birkhoff section. So recall, air covered and positively twisted, it means that the orbit space is given by this kind of picture, by the positive diagonal strip. Okay, so there is three names here for the theorem. So I found a proof of this last year after having spoken with Christian Bonatti, which was working on things which was really similar. Christian Bonatti found another proof, an independent proof. And later we found that Masayuki Asaoka also found an independent proof. So we have 3 points of view and 3 different proofs with some relation, but it's not clear if they are all equivalent. So I will present in the remaining time my point of view and my proof. So some part of the proof, not all the detail, but it will be enough at least to have a good idea on how it works. But before I will explain few consequences which I find interesting. So the corollary, the first corollary is that if you are given a transitive Anosova flow on an orientable three-manifold or oriented three-manifold, it is equivalent to a positively skewed air-covered flow up to 3 surgeries along some periodic orbit. So just to recall, so yeah. A Fritz surgery is some kind of done surgery along a closed orbit. So just to relate the Fritz surgeries with the theorem, when you're given a Birkhoff section with some boundary, if you do a surgery, along that boundary component, you can, for the new flow, you can construct a new Birkhoff section which corresponds to the old one, to the old Birkhoff section, which you just have put it in the new manifold and do what you need to do on the boundary. So you do a Fritz surgery along the boundary and you can deduce using the slope of the dent surgery if the new boundary is positive, negative, or even if you have removed the boundary component. So given a Birkhoff section which exists when the fluid is transitive, you can do some Fritz surgery along the boundary component to put all of this boundary component positive. So then you have a positive boundary component, positive Birkhoff section. Sorry. And so you have a positively skewed air cover flow. Oh, it's a mistake. So twisted, it's equivalent to skewed. Just in the word I was meaning to write skewed. Okay, and just to mention also that Christian Bonatti have a similar statement, which I believe it's even stronger. So here I just said that there is some field surgery that can transform a transitive Another flow to a positively skewed Another flow. And you can do this along the boundary component of a Birkhoff section. You can do this field surgery along the boundary component of this Birkhoff section. And Christian Bonatti can do this along other families of orbits. So there is some variation of these results. And another thing that I want to say that it's not a direct consequences, but it's just a good thing for what I will explain. So Barbeau proved that if an Another flow in dimension 3 preserves a transverse contact structure or a transverse contact form, then the flow is positively skewed or covered. So this consequences is the one I have in my theorem, in the theorem. So Barbeau proved that if it preserves a transverse contact structure, then it is positively skewed. The reciprocal direction is not understood. But now we don't have, when you have a positively skewed R-covered flow, we are not sure if up to some topological equivalence, it can be made as a rep flow. I mean, if there is some topological equivalence that transforms that flow into another flow which preserves a transverse contact structure. But at least we have this kind of open book decomposition of the flow, so open book decomposition, it's another way to say a Birkhoff section with some nice multiplicity along the boundary component. But we have this kind of surface which are relevant to study contact structure. So we don't understand the reciprocal, but maybe that this theorem is a small step towards that direction. Okay, so in the remaining time, I want to explain some idea on the proof of the theorem. I mean, for my point of view, not the point of view of Christian Bonatti or Asaoka. There is two main steps to deduce the theorem. The first one is to study some restriction in the existence of Birkhoff section for general flow. So I consider a flow on an oriented closed free manifold. And the flow need not to be another fit, it can be any kind of flow. And if it admits, so the first thing is if it admits a Birkhoff section with no boundary, Pierre Deornois in the previous talk called this kind of surface a global section. If it admits a global section, it does not admit a negative partial section. And similarly, if it admits a positive Birkhoff section, it does not admit a negative partial section. So there is some restriction in the existence of partial section, and later we'll explain that these restrictions can determine the nature of an Another flow because we know enough partial section for Another flows in dimension 3. So to give a quick proof on this proposition, so the first case is an easy case. I will explain. I mean, it's not new at all to have this kind of property. I suppose that I have a Birkhoff section with no boundary and a negative partial section. I will explain that it is not possible. So to do that, I'll compute the algebraic intersection between S and the boundary of the partial section. You compute the boundary of the partial section, and I will denote this for the algebraic intersection with the surface S. Yeah, maybe I don't have to. So the algebraic intersection between the boundary of sigma and S. So it is 0 for the reason that just because this is a boundary. If you look in to the H1 of the surface of the manifold, this corresponds to an element which is 0 in the H1 because it is the boundary of surface sigma. But although this algebraic intersection must be negative for the reason that sigma is a negative partial section. So all these boundary components here are orbit of the flow, which are oriented backward. So in that, when you compute this algebraic intersection, the orientation of the orbit are backward compared to the orientation of the flow. So every boundary component of sigma, when they intersect S with a negative sign. And since the S is a Birkhoff section, S intersect every orbit. This algebraic intersection is indeed negative, it can't be 0. Okay, so in this case, it's not possible to have these two kind of surface. So when you have a Birkhoff section without boundary, you don't have a negative partial section. So for the most interesting case, when S is a positive Birkhoff section, what do we do? So I will take the flow. I will try to transform the flow and the manifold to get into the first case. So I have a manifold, a flow. I will say a Birkhoff section S. I will say plus because it's a no, not plus. No, sorry, yes, plus. I suppose that there is a positive Birkhoff section S and a negative partial section. So what I can do is I can do some fruit surgeries. Along the boundary of S. So I mean, along each orbit in the boundary of S, I do a free surgery, dense surgery, so that the slope that I choose to do the surgery is exactly the slope of the Birkhoff section. So for each boundary component, I do a free surgery with a good slope, so that at the end, I obtain a new flow M prime, a new manifold, a new flow, a new Birkhoff section with no boundary, and a new partial section, which is still negative. So after this fruit surgery, I obtain this data with a Birkhoff section without boundary and a negative partial section. And because of the case 1, this case is not possible. So when we have a positive Birkhoff section, we don't have a negative partial section. Okay, maybe I will skip that slide. So just, I won't give all the detail for that slide, but just as a good thing is that the existence of positive Birkhoff section or of Birkhoff section without boundary or of Birkhoff section with negative Birkhoff section, this has 3 cases for flows in general that are disjoint because of this proposition, and maybe that are interesting to study in their own. And so in the view of the theorem that I'm presenting and I'm proving, these cases correspond in fact to the 3 cases in the classification of air-covered flows. So the second step to prove the theorem is to define some enough partial section for another flow so that we can relate the orbit space with the existence of some Birkhoff section. So given a flow, and particularly given its orbit space, there is a notion which is interesting to different parcel section. It's called lozenges. So morally, lozenges, it represents, so lozenges is given by 2 points in the orbit space, 2 stable leaves, 2 half stable leaves of that point, and 2 half unstable leaves, so that this unstable leaf does not intersect at infinity here, but they fit perfectly in the sense that if you enter, so here you have a simply connected component. If you enter, if an unstable leaves intersect the stable leaf in the bottom, it will leave the lozenges from by intersecting the other stable leaves. And similarly, if it enters from the left by intersecting these leaves, it will leave the lozenges by intersecting this leaf. Okay, so for example, if you have positively skewed or covered flow, given any point, you can just take the lozenges given as I'm drawing, like that. So you take its stable leaves to the right and unstable leaves to the top, and then when it intersects the boundary on the picture, you like take the next stable leaf, the closest stable leaf that have the same limit here, and you obtain here lozenges. So now that I have the notion of lozenges, there is 2 theorems that help us to produce lozenges for another flow. So I mean, not lozenges, partial section for another flow. So the first theorem is from Barbeau. If you suppose that your lozenges is based on closed orbit, so that these 2 corners correspond to closed orbits. It's enough to require that one is a closed orbit, because if one is a closed orbit, the other is also a closed orbit, correspond to a closed orbit. Then you can construct from this kind of lozenges a NIMUS partial section. So underline here, NIMUS partial section S of the flow, which whose trace is given by the losange. So we'll explain what is this trace. So I mean IMUS because it's like the same kind of surface, but we don't require the interior to be unbended. It's just an IMUS partial section. So I have this surface in the manifold M. I lift everything to the universal covering, and then I project it to the orbit space. And so when I do this thing that I take the surface in the theorem, I lift it to the universal cover and project it back, here I obtain L. I obtain the lozenges L. So I restate the theorem. If you have a lozenges whose corners correspond to closed orbits, and you do this lifting projection procedure, you obtain there exists a NIMUS partial section that such that when you do this lifting projection procedure, you obtain the lozenges L. So in particular, this NIMUS partial section intersects exactly the orbits which are given in the interior of the lozenge here. And so quickly, before I run out of time, the second theorem which interests me is that it's not a theorem, it's just a part of the theorem from Fenley. When the flow is not air-covered, there exists a point which corresponds to a closed orbit here, such that there exists lozenges in the 2 quadrants of the points. So here you have a quadrant plus plus. I mean, this lozenges is in the quadrant plus plus, I mean, right top relatively to that point. And here there is another lozenges, the gradient plus minus, so left top. So when the flow is not air covered, there exists this kind of lozenges. Okay, so I'm running out of time. I will explain quickly maybe the interesting direction, which is this one, the first one. I suppose that I have a positive Birkhoff section and I want to prove that the flow is positively skewed. So there is 4 cases. I won't explain all the cases, but there is 4 cases that I will give. Plus skewed, the flow can be positively skewed, can be negatively skewed, it can be trivially skewed. I mean, trivially skewed is the other case in the classification of the orbit space, or it can be non-air covered. So quickly, when the flow is trivially skewed, so it's a result from Solodov that this flow is topologically equivalent to a suspension flow. In particular, it admits a Birkhoff section without boundary, and it's not possible to have a positive Birkhoff section and a Birkhoff section without boundary. So this case is not possible. And in these two other cases, no, it's not these two cases. In the case minus skewed and non-air covered, there exists some lozenges which are in the quadrants plus minus of a point of a closed orbit. So there is this kind of lozenges. And from this kind of lozenges, you can create a negative partial section. So this is a result from Barbeau. From these lozenges, you can construct a negative Eimers partial section. I mean, you can construct an Eimers partial section, which happen to be negative. And you can desingularize, as I've explained Pierre Dornoy in the previous talk. You can desingularize this Eimers partial section into a partial section. And so we obtain a negative partial section, which contradicts the fact that there exists a positive Birkhoff section. So these two cases are not possible. And the only remaining cases is that the flow is positively skewed air covered. So I won't give the detail for the other because I've run out of time, but the idea is just to cover the manifold using lozenges and to construct a Birkhoff section, a nice Birkhoff section using lozenges. So yeah, probably does not make any sense if I don't give the details, but I will stop here. But thank you for your attention. Okay, so do you have any question?
Thank you for your report.
Do I understand correctly that now it's my turn to enter? So are there any questions? Okay, it's a bit late, and let us go for a break right now. It will be, if I'm not mistaken, 11 minutes break. And in these 11 minutes, I think that whoever wants to ask a question will have this opportunity for this 11 minutes. And let us reconvene in 11 minutes from now. So Boris, you are next. So
Good.
You are already co-host, right?
Let me quickly check. Actually, I should just try to share a screen. And yes, you are the co-host now, says Zoom.
Yes.
So I already feel incredibly powerful, which is good.
Does this 2 minutes of glory when everything belongs to you?
And let me see whether it actually works as intended. See something here. Good. And even better now. Well, it looks hopefully pretty okay. What do you think?
Yeah,
Yes,
I think
okay.
it looks perfect. I think it looks perfect. I have a question. Maybe I'm not the only one, but somehow, Alexei, I think it's on your side. Maybe I'm wrong on the options of Zoom. So somehow I don't know whether it's everybody, but I, for example, see only Boris on the side and not.
No, this is on your side. So
it's on my side. Okay.
yes, at the top right corner you have
View.
View. Yes, and in this view you can
I
do
see.
something like gallery or so.
Gallery. Yeah. Okay. Now I see.
Yes, it's nice, right?
Yeah. I'm still not. I'm
It's
very.
always changing. So
Right. The pandemic has not been long enough yet, right?
I'm very anti-technology person. I mean, can you please give me back my blackboard? And when I'm saying blackboard, I literally mean blackboard, not the whiteboard. Please, blackboard. So is it possible?
During the few minutes we have, may I ask some question for the Russian community? You know, Theo Marty spoke about Solodov theorem. So Solodov is some name which now is very popular, either in group action or in Anosova flows. We don't know him. So he's still active, still in the dynamical field. Why did we never see him in any meeting?
I don't know him in any way, but the problem is that it is quite popular Russian surname. So probably if you have any
it's a VV.
any reference, I can start to search from this. So you can just write me, and I'll try to find out which Solodov it was and so on. What is very
I think if Slava Granit is there, so he has some work with Slava.
Maybe Slava knows something.
Although you don't know him?
I'm here.
What question, Оля? Скажи мне,
Христиан спрашивает, вот Солодов, у которого есть совместная работа с Аносовым, он кто? Он жив, не жив, действующий математик? Или
ничего не знаю. Я знаю только, что Аносов на него обижен, и все.
За что?
Ну, там что-то не то у него было.
Но об этом я думаю, не надо.
Да, но вот тем не менее... Да.
Он жив, не жив, нет, вы не знаете, да?
I don't know, from very long time I never hear about him, unfortunately. I don't know.
He stopped working on math, or?
Indeed, we don't know. It seems.
Okay.
I don't know at all.
I even don't know whom I can ask about it. Maybe all people go out, unfortunately.
Okay.
Stepin and Plikin and so who else? Maybe Zhirov. Maybe I try to ask somebody about it.
Thank you.
Is the lockdown in Moscow over already?
Good question.
Well, it's Schrödinger lockdown. It is the same time in place and not.
I know exactly what Schrödinger lockdown means. I'm a Schrödinger person, so that's my bread and butter to know what it means. So it's not over.
Yes.
That's a pity. It would be much easier to be actually at the conference instead of Zoom. I think a lot of people will agree with me.
Yes.
Yeah, that was a nice opportunity to disappear to somewhere.
Yes. Yeah, I mean, there are some virtue to online meetings. Sometimes allow people to participate who couldn't otherwise come.
Yeah,
but there are also things one is really missing in a Zoom meeting compared to being in the same place together.
Yes, and it's also absolutely, I find it, I mean, here's the week of conference and I'm listening to all the talks and everything. And sometimes I do want to ask a question, but I'm stopping myself because I know that it's not a question for actually the talk. It is something that I would be very glad to ask during coffee.
Yes.
This person to the board and asking him, okay, so there was this technical detail which I missed. So please, can you start from the beginning?
Mm-hmm. Absolutely.
That's something which is I think extremely messed up with all this technology. I mean, we say that we actually gain from technology, but we never say how much we miss.
Well, we will really gain once we can have meetings in person when we choose, and meetings by Zoom if we choose. This time it wasn't by choice, so we lose. But having both options adds something, right? You're right that in a Zoom meeting there's something missing that's really important, and that's why I prefer to be at an in-person meeting. But at the same time, sometimes you get people in a Zoom meeting who wouldn't be able to make it to an in-person meeting. So it's upsides to both, but I'm with you. It's the unstructured time outside of talks that's really valuable when people are together in one place. And yes, that there's no substitute.
Okay, I think it is a time to start. So we're starting our afternoon session. So welcome everybody back. And we're starting this with a talk by Boris Hazelblatt, and who from Tufts University, and he will tell us about surgery at contact flows, hyperbolicity, and orbit growth. Please.
Thank you. Thank you for the introduction. Thank you for the invitation to participate in this great celebration. It has been a wonderful visit to Moscow. I've really enjoyed it. And I also thank the organizers for scheduling me at this time, because being this late in the week allows me to shamelessly assume that everybody has attended and fully understood and entirely memorized each one of the preceding talks, so that you have the best prerequisites for everything that I intend to say today. I'd like to particularly thank Christian Bonatti, Andrei Gogolyov, and the preceding speakers today for saying things that are highly relevant for what I was going to say today. So then, Anosov has a big footprint, and I think it's good to start with a bit of context, given that Anosov is also in the talk of my title and he's being celebrated here. Andrei Gogolev showed the Russian version of the famous book. This is the English translation, which I've had for a very long time, not quite since 1969. And that was maybe what one would in other places call the habilitation, I gather, of his, which is where he put his name on Anosov flows by really putting together a variety of things, one of which was the motivation coming from Eberhard Hopf and ergodicity of geodesic flows in negative curvature, not necessarily constant, which inspired Anosov to extract the hyperbolic features of that flow as the essential element. Another story that was recounted earlier this week is about the 1961 Kiev Symposium, where Smail visited, and Smail had told Novikov in advance of that symposium, and that created a whole travel group from Moscow, including Anosov, who attended to hear from Smail, and this apparently really was central to bringing, in addition, the idea of structural stability in play as being connected to hyperbolicity. Smail's image, of course, was the famous horseshoe, which made him realize that structural stability doesn't hold only for more Smail systems. I did mention on Wednesday this article Anatol Katok wrote about Anosov for a nice anniversary volume a little while ago. It makes great reading because it is about his life in mathematics. It brings to life in a wonderful way Anosov, the person. Katok generally was a great chronicler of many of the things he experienced, and another article I recommend is on Moscow dynamic seminars of the 1970s and the early career of Yasha Pesin. That also includes lots of really wonderful things about Anosov and what he has done for mathematicians, the community, and for mathematics. I'm going to jump fast forward a little bit to a question about Anosov flows that has engendered a lot of mathematics, and this talk is a bit of a tangent from there. In 1981, Anatol Katok looked at geodesic flows on surfaces. And you don't need to understand all the notation here, but he says what he proves there in the first line is that to the right of these various inequalities is a quantity that involves the Euler characteristic, so topological quantity associated with the surface. And he shows that topological entropy of the geodesic flow on that surface will exceed this topological number. And then he shows that, in fact, the Liouville entropy is guaranteed to be no more than that quantity. And any of these inequalities becoming an equality happens only for constant curvature. So that is an early rigidity theorem for geodesic flows, that metrics of constant curvature are distinguished by the coincidence in particular of Liouville and topological entropies of the geodesic flow. I'll just mention that in that same paper, he did, with the help of Ralph Spazio, compute the topological Liouville entropies for symmetric spaces and found that they coincide in all those cases. And so he remarked that it looks like a reasonable conjecture that those, meaning symmetric spaces, are the only case of manifolds of negative curvature for which these two entropies actually coincide. That's since been known as the entropy rigidity conjecture of Katok, as opposed to some other entropy conjectures. And it's still open. Opinions are divided on whether it's true or not, but there we are. What I want to take as my starting point is a theorem by Foulon, close to 20 years after Katok's original theorem, inspired by work in which Foulon was engaged with others, Benoit and Labourie. So this theorem pushes the Katok theorem in the following way. It says, let's just look at a contact Anosov flow, and I'll define these, but by the time you've gotten to this week, you certainly know what an Anosov flow is. I'll talk about contact presently. On a three manifold, geodesic flows are examples of that. If the two entropies coincide, then up to finite covers, that flow is going to be smoothly conjugate to the geodesic flow on a closed surface of constant negative curvature. Well, so that looks like an echo of the theorem at the top. The thing, of course, is this is talking about a flow rather than about geodesic flow, so one cannot talk about the manifold being the same. But this says that dynamically, a contact flow for which these two entropies coincide is the geodesic flow of a hyperbolic surface. The question that arose from this theorem, but actually from that prior work I mentioned, but I'm not going to make explicit, is there is some amazing thing here, which is that unlike in the case of Katok's theorem, where you talk about geodesic flows in Riemannian metrics, this theorem starts with a contact Anosova flow, and out of all the ingredients magically constructs an underlying surface with a geodesic flow to which the Anosova flow about the theorem talks is conjugate. So topologically, the conclusion is that this contact flow lives on a manifold, which is a unitangent bundle of a surface, which has a constantly curved metric. That's not an easy thing to show. And one question that arose in trying to prove this, literally among Foulon and his co-authors for the other work that's similar in spirit, is, does the contact property by itself already force the structure of a geodesic flow here? Or is it the entropies that do? So that's the question that's motivating here. If you look at contact Anosova flows on three manifolds, are they necessarily geodesic flows? Well, so Foulon thought about this and did come up with a surgery in the contact realm, which we wrote up together, which produces contact Anosova flows that are not of that type. So the question has a negative answer. It's really the coincidence of entropies that forces the structure of a geodesic flow, not the contact property by itself. And I'll describe that surgery in slightly more detail, but I'll mention a few properties of these Anosova flows that are interesting. And again, those who've been to the previous talks this week will find some of them less surprising than others. But in particular here, the properties you get when you start from that geodesic flow of a hyperbolic surface, you no longer have a unitangent bundle. So topologically, you're not orbit equivalent to an algebraic flow. I'll define that, but that means not a geodesic flow. The Anosova splitting is necessarily non-smooth. That's a contrapositive of a known rigidity result. And also the two entropies can't be the same because of Foulon's result on the previous page, right? If they agree, then you've got a geodesic flow. So if this isn't a geodesic flow, you've got different entropies. You can't make them equal by tweaking in any way whatsoever. I admitted here, this is a result that's not terribly new, but there are some new things we realized about these. So to give a quick view of the ideas I want to breeze through today, the surgery that Foulon thought up turned out to not have been entirely new. Geometrically, topologically, or smoothly, it was known. He started from Handel-Thurston surgery, about which you've heard earlier this week, if you attended the right talks. But Foulon's idea was to make it into contact surgery that preserves the contact property when you start from geodesic flow. And we learned much later that, in fact, people in the contact world had thought of surgeries much like these, and that's why I added the names of Ding, Geiges, and Weinstein. I want to talk a bit about how the surgery by itself forces orbit complexity or added orbit complexity. That's the newer thing. And also how, if you start not from the geodesic flow, but from something else, you can construct interesting new flows. In particular, if you take the fiber flow of a surface, which is this trivial periodic flow spinning around unit circles, you can actually, by this surgery applied to that flow, create non-trivial topological complexity. The other thing that is newer than 2012 is that when you do this to the geodesic flow, the flow has a property, well, you get a contact structure, which I'll define as well in a minute, where every flow that respects it has positive entropy, not just the flow you constructed, but any flow that preserves the structure is necessarily exponentially complex, which is rather interesting. Again, increased orbit growth, meaning increased topological complexity thanks to the surgery. And also in the end, you'll see that there are some manifolds that the surgery produces, where we have two contact flows, of which one is exponentially complex, basically Anosov, and another one polynomial complex, which is interesting. I'll just recall that much of this week, this talk is entirely three-dimensional. Quick definitions. Anosov is known, so maybe I'll just note that that's here on the page. The contact property is that, well, the way I grew up saying it is a flow preserves a contact form. My definition is slightly more specific, pretty close to equivalent. So one form on, let's be specific, a three-manifold is said to be contact form if it's totally non-degenerate, which means that if you do the exterior product with its exterior derivative, that's a three form, that's a volume, meaning nowhere zero. That's the non-degeneracy assumption that makes it a contact form as opposed to some other one form. Once you have contact form, there's a canonical vector field and flow associated with it in the following way. The kernel of dA is going to be one-dimensional. That's the non-degeneracy condition. So saying that your vector field is supposed to be in that kernel defines the vector field up to a factor. And then saying that form applied to vector field is 1 picks the exact vector. So this is the canonical Reb, or characteristic vector field, for such a contact form. It creates a flow, which then is called the Reb flow for this contact form, and that flow will preserve that contact form. Another flow is defined in the middle. By now, I trust we've all seen enough of those today. This week, in fact, and algebraic for this talk means that your flow is finitely covered by the geodesic flow of a surface. Other algebraic flows are suspensions, but contact flows are never suspensions. So for what I'm talking about, that's not in scope. So again, there's plenty of Anosov flows. We heard a great arc of that story when Christian Bonatti talked about it. In fact, as the three Bonatti, Béguin, and you who put together this Lego construction of all manner of Anosov flows on three manifolds. That is fairly recent, but a lot of these surgeries were around in the 90s already, and experts, some of them anyway, weren't sure that in the contact category you could produce all these. So the novelty of the surgery here is that it's making Handel-Thurston surgery slightly better in that you can actually start from a contact flow and retain the contact property. And that's actually just a bit of clever deformation to make it go, and I'll show a little bit about that. Just again, more about the properties of these flows that wind up being constructed here, contact flows to be specific. We will show in particular that there is exponentially more closed orbits than for the geodesic flow, and I'll have to explain, of course, what that actually means, even in one homology class. So there's a lot of more periodic stuff going on in a variety of ways. In fact, if you do the surgery in a fairly aggressive way, you can produce as an output a three-manifold, which is hyperbolic in the sense of Thurston. And in that case, it turns out that every closed orbit for your newly constructed Anosov flow is isotopic to infinitely many others, which I found rather mind-boggling, having thought only about geodesic flows and suspensions. Suddenly, you've got all these different periodic orbits which are pairwise isotopic. That's quite remarkable. And again, that just the contact structure you get alone forces necessarily exponential orbit complexity and the like. So many thanks to Marty for talking about the Barbeau theory of Anosov flows in 3 dimension, in particular the R-covered ones. He told us that they come in 2 main flavors, one of which is that if you go to the orbit space, so then that means we go to the universal cover of our underlying manifold. And when you think about geodesic flows, when I think about universal cover, I think, oh, let's now think about the unit cover, tangent bundle of the universal cover of the manifold. But that's not what's happening here. We're here talking about the universal cover of the phase space, which for geodesic flow would be the universal cover of the unit tangent bundle, rather than the unit tangent bundle of a universal cover. So what we learned is that, that's a plane and that you can factor out by orbits. So you do a three-dimensional thing, you can factor out by orbits when you're in this universal cover. That gives you something planar, inside which the leaves project to these things labeled with L as in leaf. And the suspension case is the left one, where you get this beautiful rectangular grid and everything goes off to infinity, or to, into a square with boundary being infinity. But when you start from geodesic flows, and more generally, always when you look at a contact flow, you'll have this skewed structure where here I've just shown them at an angle, but I mean the top and bottom to be really ends, whereas left-right things extend. In fact, these are better pictures, which will look familiar to those who were here in the previous hour. These are borrowed from Thomas Barthelemy, who wrote a wonderful survey of this entire subject. I highly recommend it. You might want to look for it on his webpage. So for contact flows, skewed or covered flows, positively skewed in this case, stable and unstable leaves in the orbit space look like I've depicted them here. The global picture, as it were, is on the left, where you've got this meandering river going in this northeast direction. And this picture is quite suitable to giving an idea where these infinitely many pairwise isotopic periodic orbits come from, which is you simply do a lozenge. Pick a periodic point, make it the vertex of a lozenge. That's what's happening on the right here. Quick check, can you see my cursor moving around? I get a nod, thank you. So then, here's my little O, a periodic orbit. I go to north until I hit the top, and then I turn right for my green line. At the same time, I go east, and when I hit the wall, I go north, and the new intersection point is another periodic orbit, the other vertex of that lozenge. And it turns out those are homotopic, and Barthelemy showed they're actually isotopic, which is wonderful. By the way, this means that there's no knot theory for closed orbits in this context. A very cool dissertation. Now I'll talk about that surgery a little bit. You've heard about surgeries quite a bit. My mission here is to make it explicit in a way that you can believe that one can do this in a way without breaking a contact structure, including explaining what the additional idea is. I'm going to be very specific about how the surgery is set up, although in fact it can be done in some generality in contact flows, in fact for contact structures. So think about, let me just quickly rewind. Let's think about the double torus as my preferred surface that has a metric of curvature -1. And that, of course, has this central waist where these various multicolored things meet. And so this is just meant to be the middle portion of this hyperbolic surface. And my surgery will be on the unitangent bundle. So let me pick, first of all, a circle in the unitangent bundle. And the way I pick it is I take a closed geodesic that separates this torus into two halves. And I take not its tangent, but its normal vector field. That gives me a circle in the unitangent bundle, which is transverse to the flow because I'm at 90 degrees. In fact, I need an annulus to do surgery. Maybe a full torus, but an annulus will be good enough. So in fact, I think about that normal vector plus minus a little angle. That defines an annulus in the unitangent bundle, nicely embedded. Here is that same picture, where in slightly lighter color, you see that annulus, but as part of the full torus, which is the closed geodesic, with all its tangent vectors. So what you see here is in fact, a meridian of this sort. And the surgery that we're going to undertake, we have this, angle variable bit here, just a little something, I'll call that variable W, and take a close look at this meridian before surgery and after surgery. It's going to spin around once, or in fact multiple times, in the this direction, which is a parameter along the geodesic. The closed geodesic that separates the two halves. Okay, let's take a quick breath here because I want to return to the fact that we want to study the contact structure preserved by the original geodesic flow. And here we go. We have a contact structure. Remember, that's supposed to be one form, wedge, its exterior derivative giving a volume. And it turns out we're transverse to the flow, so in fact, nicely to the contact structure. There are canonical coordinates which have the name Darboux attached to them for classical reasons. I'll just be specific. On this annulus, I'll choose coordinates S, which is the S1 parameter for the closed geodesic that defined the initial circle, and W between plus minus epsilon is that little angle, how far I deviate from the normal. That is an annulus. And with a proper choice of S and W, if I also think about T as a variable along the flow, right? We have this little annulus transverse to the flow. Now thicken that a little bit by moving the time direction. My contact form, the canonical contact form for the geodesic flow in the right choice of coordinates actually is going to be literally dt plus WDS. And here's the check. You do the exterior derivative, you get just dW wedge ds when you do this. And if you wedge that with A itself, you get dt wedge dW wedge ds, which is as wonderful as it gets for being a volume. So these are canonical coordinates. And these are essentially the coordinates you get from the usual business when you do geodesic flows, Sasaki metric and standard coordinates. The surgery in pictures here is literally just the Handel-Thurston surgery. I've just extracted from the previous picture the annulus only, so we can see what's happened around the annulus minus the entire fiber torus there. And you see in black here exactly what happened to meridian. It just spins around once or maybe multiple times. And in formulas and coordinates here in the box, you see what I'm doing is my S circle variable and W goes to same W variable, but I'm spinning around the circle with my function of W once, or in fact, in the end, Q times, however many times I want. And I could make that explicit with, a little exponential expression or something, as I do here. So that's literally our spinning around. Right, so actually, sorry, I skipped a little bit too fast. One cool thing that one can easily check is if you look at this big F, which does what I said in the box, and you pull back your A wedge dA, your canonical contact volume, it turns out it's preserved, which is wonderful. It's also not new. Handel and Thurston remarked their surgery applied to volume preserving flow will give you volume preserving flow. I'm just saying that here you see that directly from a computation as opposed to other considerations. There is a problem though, and that's why the question arose. If you do the surgery and you see what happens when you pull back the contact form itself with the surgery rather than the induced volume, there is an extra term that happens to disappear when you wedge with dA, but it's really there, and that means that, in local coordinates, one side or the other, things don't match up. You don't have a well-defined anything on the surgered manifold. Poof, there goes your contact form. And Foulon's idea was, well, when you hit a speed bump on the road, you hit the brakes. So we're going to change time. And never mind this complicated integral expression, just think there's an H that does the right kind of thing, whose DH is half of the blue thing here, half of the problem. And if you then pull back A sub H, which is A plus DH on one side of the surgery and A minus DH on the other side of the surgery, and you just see what various things happen here, it turns out that you split the difference just right. You pull back A minus DH, run a calculation, and you get A plus DH on the other side, which was your definition of A sub H. So suddenly we have a well-defined contact form on the surgered manifold, and all it took was a gentle deformation to prepare for the disruption of the surgery. A minor problem, of course, is we've changed the contact form, so we have to adjust our vector field, so it preserves that. It turns out, well, the most obvious possible time change does actually do exactly the right thing. 1 plus minus dH of the vector itself as a scale factor does what we need. Cool. So that's Foulon's idea, which again, we noticed that contact folks had been thinking about things of these types for a while, and there we go. I want to now talk again about hyperbolicity. After all, that's what this conference is all about, right? So we do the surgery, and one thing is, okay, I have a new contact flow. Another one is, do I have an Anosova flow? Bit of an afterthought. And the answer is, well, sometimes yes, sometimes no. If you spin in the right direction, you'll actually be fine. It turns out if you take, in my notation, positive Q, then things are good. Otherwise, you may have a problem. And it's really looking at cones that tells us that. and preview of what we're going to see that goes a little bit beyond just the hyperbolicity of the surgery flow, which is, of course, a basic idea, is that Lyapunov exponents are going to be no less after a surgery. There's an extra kick. And that gives us a first hint at maybe the complexity is actually going up as a result of this surgery. So I get larger Lyapunov exponents, picture coming in just a second, which tells me that by Pearson's entropy formula, the Liouville entropy of the surgery flow is going to be no less than the original one. Here's a picture to go with it. And this is a picture that will resonate with those who were in the talk by Keith Burns, where you saw the unstable cone being the positive quadrant with the horizontal direction, horizontal in the sense of Riemannian geometry being horizontal in this picture, and the vertical direction, again in the sense of Riemannian geometry, being the vertical one, and the unstable direction will, in the curvature -1 case, be literally exactly the diagonal. So I call that E plus, it's literally V plus H. In the, add V vectors plus some H vector, so that literally diagonal is the thing. Oh yes, and what does a surgery look like? Well, remember it's a shear. I could snap back to pictures, but that's not very happy with Zoom usually. But remember what I do in this little annual is literally the shear. I spin around once. That's what you do in Dane surgery, which means the differential is literally a shear. And if you have hyperbolic dynamics that moves things more into cones, and then you hit the surgery, what we're doing is, here's the green thing, a vector is being further displaced by being moved to the right. If your shear is positive, things move to the right in the upper half plane, which means that if you look at its unstable component, right, for a given prior unstable component, that's the blue dashed line here, shearing in the horizontal direction and to the right increases the unstable component, which is just the kind of thing that makes sure the Lyapunov exponents are no less than they were if you just do your hyperbolic thing alone. So that is a cool thing, that what preserves hyperbolicity also guarantees that you have no less hyperbolicity, as it were, because the surgery shear kicks in the same direction as the dynamics in the cones. So more expansion, more entropy. Let me make that just a tad sharper. All right. So I'm going to do lots of playing around with geodesic flow originally, surgery flow, and then Liouville entropy and topological entropy. So I'm starting on the left of this string of things with the topological entropy of the original geodesic flow. And because it has constant curvature, that's the same as the Liouville entropy of the original geodesic flow. Now I take that geodesic flow and I do my Foulon, Handel, Thurston surgery on it, which, as I just explained, means that the Lyapunov exponents after surgery are no less. So I get an inequality, and my Liouville entropy has not gone down. Oh, and now the theorem that motivated this whole talk turns out to be also useful in it, because a contrapositive Foulon's theorem is that since we are not topologically the same as a geodesic flow, the topological entropy of our final flow must be strictly bigger than its Liouville entropy. Which means that if you look at the very left and the very right of these, we have shown that we have a strict inequality between original topological entropy and surgered topological entropy. We have strictly more exponential complexity, which, as we know in hyperbolic dynamics, means strictly larger periodic orbit growth, which is very cool. The surgery alone actually forces orbit growth. This is something where I'm stretching my expertise. I mentioned in our first slide that this work is joined with Patrick Foulon and with Anne Vaughan in Ossay, or now Saclay. And she contributed enormously by bringing contact homology into this picture. And in particular, that gives rather remarkable statements, which is that for any contact form that's compatible with a given contact structure that results from the surgery, you can actually give lower bounds on how many of these pairwise homotopic periodic orbits you have in any one homotopy class. I said there are infinitely many, but in fact, there is a lower bound in the growth rate. Fundamentally, that came by Bartonley and Fenley for a specific flow. The remarkable thing is, if you take any other flow that preserves the same kind of contact structure, that's automatically the case. You can't avoid it. There's something topologically or contact topologically forcing this remarkable growth. In fact, even without assuming that anything is hyperbolic, you get something. So we do the surgery on something. We do not assume that we do surgery in such an aggressive way that our resulting manifold is hyperbolic. I don't even assume that I have an Anosova flow. I might have the wrong sign for Q, and I don't have invariant Cohen's hyperbolicity and all that. Nonetheless, after surgery, we've got this contact structure there. Any rape flow associated with that contact structure will have positive entropy. So there's something that forces the contact structure itself to produce exponential complexity, never mind any kind of hyperbolicity as we understand it. Rather remarkable. I can't give you much of an idea of how this works. But I do want to talk a little bit more about fun other things we can do with the surgery. I hinted at this earlier, but I think I buried that earlier hint by focusing so much on Anosova flows and hyperbolicity. So playing quickly with the basic algebraic structure of this hyperbolic surface, we have, as previously mentioned, a horizontal vector field or horizontal direction. We also have a vertical one. And also canonical is the geodesic vector field that you have associated with the Riemannian manifold. Actually, the definition in this case for horizontal would simply be, let's take the Lie bracket of vertical and geodesic direction. That can be taken as definition of horizontal. In the SL2 representation, that is the 1/2 anti-diagonal matrix. If you Lie bracket horizontal and geodesic, you get the vertical direction. That's the fiber direction for the unitangent bundle. And that's anti-diagonal, but the -1/2, so that's generates rotations. And if you take the horizontal and vertical, their bracket is the geodesic direction, which is the diagonal matrix with 1/2 for expanding and -1/2 for contracting. I just wanted to write these down because it turns out just by doing exterior calculus on a few of these, one gets interesting stuff. So for instance, if, remember there was my original A contact form, canonical one associated with geodesic flow, it turns out if you stick V into dA, vertical into my standard thingy here, that gives me a one form, right? One slot is still open. That turns out to be a contact form, and its rate field is a horizontal vector field. So it turns out that there is a horizontal flow, which is a contact flow, and that's just sort of built into here. It turns out that, well, you don't have to be horizontal. If you do any linear combination of horizontal and vertical, that is a rate flow of something. Put differently, if I take my A, the canonical contact form for the geodesic flow, and I take the B that I just introduced, and I do, the cosine sine linear combination of these, just to think about a circle here, there's a rate flow for each one of these because they turn out to be contact as well. You're just interpolating contact forms with the same orientation. So it turns out we have an S1 family of Anosova flows. Here's a little computation that proves that these are Anosova flows, all of them. Okay, let's just go back to thinking about this more elementary ways. It's a cool computation, and why not? What's really going on is, here is my S1 family of Anosova flows. My geodesic flow takes a tangent vector and moves it along a geodesic. This S1 family takes vectors at angle theta and moves it along that geodesic. And right there, you've got an S1 family, right? Instead of moving a tangent vector parallel along a geodesic, just take an angle something vector and do the same thing. It's obviously structurally going to be exactly the same as the geodesic flow. So it's adorable that there's an S1 family of Anosova flows here, but it's elementary and not really very interesting. However, it does get interesting if I play the same game with my dA, but I stick the horizontal thing in there. Turns out that gives a contact form. I'll call that C. Happens to be contact, but it's just the next letter after C as well. Contact form, therefore it has a rate field. And in the department of the unsurprising, that is a flow we saw before. It's simply the fiber rotation. So the novelty for me here is that when
4 minutes left.
4 minutes. We'll make it. Thank you. When we look at this flow, the fiber rotation, it's not a new flow, but it's interesting that actually that is in the contact realm. That's sort of cool. I'm sure that's not new, but it's sort of interesting that it's one of these examples. And on that, I can now do surgery, right? I just talked about the stuff I can do in the hyperbolic surface. I have this trivial periodic fiber flow, but the novel idea is never mind the geodesic flow now, apply the same surgery idea, which works generally for contact flows, but to this fiber flow, which again, dynamically is totally trivial, completely periodic. If we use a simple geodesic, then in fact, this is sort of a badly ignored picture of what this might look like. It turns out, the periodic dynamics remains periodic, totally trivial, but orbits, fibers that hit this blue annulus here experience a shear, and so what you get is parabolic dynamics. Okay, so out of surgery alone, we get some orbit growth. Now it's quadratic because what we have is shear type dynamics. What is cool, and by the way, when you do that, it turns out that any contact structure of the same flavor produces a flow which has at least quadratic growth, so you can do this contact homology on that as well, which is rather exciting and nifty. But the other thing that's interesting in that is not yet written up. Project in the air right now, which is supposed we take a geodesic that ain't simple, so it has a self-intersection someplace, so you get this annulus, which in this picture that shows the surface looks like it self-intersects, but remember we're doing it in the phase space in the fiber bundle. So in fact what I see here, this literally photo of a blackboard picture, is I get this racetrack which has an overpass, because when you go in this direction versus in that direction, you're at different altitudes in the fiber. So there's no actual annular self-intersection, but in projection, there is this overlap, this overpass. And the cool thing is now you get shear dynamics, but when you are in this region here, as you go through, you get a shear in one direction, and very soon after you get a shear in a complementary direction. Here is just a linear computation that suggests what happens. You take a shear, you take another shear, and when you do the composition, you can actually look at this matrix. It turns out that's hyperbolic. So these two shears can combine to give hyperbolicity. The name for this kind of thing is called linked twist maps, and that they give hyperbolicity is fairly simple. The one thing is we are constrained here about how we link them, and unfortunately in a way that's not co-oriented in the way that people usually think about, which makes them not all hyperbolic. Here's a picture that Curtis Heberle drew, a doctoral student in my department. He has since become an algebraic geometer, but he's still planning to write up his insights about this, which are, he didn't draw this for publication, so don't tell him that I showed this picture publicly. Here is the rectangle, which is the overlap region of this overpass. And what he has drawn in here is if you pick the right kind of rectangle, and he's a red and blue color coding, which is not stable, unstable, it's just what it is. If you look at how things are sheared, when you do the spinning around in this way and the overlap, what you do get is something that's literally a horseshoe, that you get these snakes going through and crossing, again, in projection, which gives you horseshoe-like dynamics. So in particular, that means that he has a proof that this surgery on the strictly periodic flow with a non-simple geodesic necessarily gives you a horseshoe, so exponential orbit growth, hyperbolicity, and all that. Slightly trickier project undertaken by another student who is still hoping to put that together. That's in the initial stages as opposed to in the write-up stages. Is can we look at the restriction to fibers that meet the surgery region and establish that that is altogether non-uniformly hyperbolic, as opposed to just containing a horseshoe? Is there more going on? It sounds vaguely plausible. There's work by Prititsky that gives a good template for it. As yet, I only can say with some certainty that if one does things linear, so the flow isn't particularly smooth, this ought to work. The shear slowing down at the edges is a little bit of a difficulty. Good. I think I'm told that I'm very near time, but I'll just...
1 minute.
1 minute. So in that minute, I'll just say something about what hasn't been done. Attempted but not done is, there is this entropy gap, and I said we have bigger entropy after surgery because of Foulon's theorem. That's a contrapositive of a rigidity theorem, which means we have no idea how big that gap is. How much entropy does a surgery produce? No idea. So one could try to make that sharp. And one idea might be, and that's been totally unexplored, can one make this shear hyperbolicity idea work in any way to give an actual gap in the Liouville entropies? What does a surgery do to Lyapunov exponents? I don't know, would be cool, but I can't say. And full entropy rigidity, you can't do very much. So then, but here is an idea that uses a bit of geometry about making this gap bigger. This was something people thought about some 4 years ago. It does seem to be rather tricky, and they moved on to other things. And that's simply, let's take a different look at the surgery. Let's look at the octagon that defines the hyperbolic surface we're looking at, genus 2. The separating geodesic, when you look at the universal cover, is an equator of that octagon here. And once again, this is literally, in this case, a whiteboard picture that Kurt Vinage drew. One way of describing the surgery, when you keep in mind that there is a configuration space for the flow, is you've got a geodesic coming and hitting this region. Remember what our surgery does? It moves in the base direction, depending on where you're in the fiber. So depending on which angle you have, you get kicked in your base point and then emerge with the same angle. And if you have many, many twists, that means that for a given point at which you arrive and a relatively small angle range of arrival, you have lots of exit points at your disposal. And you can certainly see that done right, that might give you a quantifiable way in which the combinatorial complexity goes up, right? Instead of exiting in the same point and necessarily hitting here for a given angle, for tiny angle range, instead of hitting here post-surgery, you might hit any one of these. Maybe that's a way of quantifying a growth in exponential complexity. But frankly, they realized that there are challenges to carrying this out. And therefore, I think if anyone here wants to take up that project, enjoy. Once again, thank you very much for your attention, for the invitation. Like I said, it's been a wonderful visit in Moscow. Thank you.
Thank you very much. Let's thank our speaker. Are there any questions?
I have several questions, but maybe I will only ask 2 of them. Is there a similar construction when you have a Goodman surgery to extend it to some kind of
that's an excellent question, and that's one that Patrick and I really tried to do. And at this point, I can't really say. I tried to make it work, and we spent some time. And the challenge turns out to be that in this situation with this Sandel-Thurston surgery, transversality of a natural annulus with which to do this to the flow, in fact, contact orthogonality is right there. And with the Goodman surgery, we seem fairly far from transversality. In fact, not transverse. And so it was unclear to me how to make it work. I have a vague recollection that some people have realized that one can push this in that direction, but we ourselves weren't successful.
Okay. So my following question does not make sense, but I still ask it. If anytime soon you can understand this kind of Goodman contact surgery, do you think that when it makes sense that you will still have this kind of gap in the entropy? Like does the difference between the Liouville and the topological entropy will...
Yes, I mean, there's a Foulon gap, and that is what it is. But yes, can I say something about Lyapunov exponents going up? I don't know for sure, but I am inclined to conjecture that the answer ought to be yes, simply because when you do want to prove invariance of cones, under a kind of surgery construction, which in this case preserves contact, one would hope as well, it seems natural that whatever you do to preserve cones is not going to reduce your unstable expansion. That's not an argument, but that's my expectation of how it would go to establish hyperbolicity of the flow after surgery, that will hopefully tend to be in a direction that also gives you no less Lyapunov exponents. But if there's a more clever proof that doesn't do that in a barehanded way, that may not be obvious.
Okay.
Okay, so are there any more questions? If not, then let us take a break of, right now we have 15 minutes break, and we will reconvene at, I want to say 4, but it's 6 Moscow time, so 4 London time. We will reconvene in 15 minutes from now. There will be a next talk by Ruihan.
Excellent. Thank you all.
Rui, are you here?
Yes, yes.
Then I think you should start preparing for your talk.
Oh yeah, let me.
You need to,
my iPad.
they will probably make you a co-host, and you need to start to prepare a new share screen.
Just a moment. Yes, we'll do
Hopefully
this.
you prepared your talk long ago.
I need to join with my iPad.
Yeah, then you will just share screen. So, and then.
Right. 1 second. Seven, 8, 5, 2, 3.
Wait, Alexei, I would say wait, because probably you're making the wrong Rihan co-host.
And both co-hosts.
Yeah, so he once he will connect to the Zoom via iPad, then
yes, that's okay. Yes,
it's
well-known technology. Okay.
I'm always laughing when I'm teaching. There are 3 of me in Zoom.
That sounds like an identity crisis.
That's because of that's what iPad does if you connect with audio to the iPad.
Hello?
So have you managed free?
What? Yeah. My iPad is in.
Okay, then do the share screening, and I will take a.
Ира, сделать второго Руйхана тоже. Окей.
Да, именно что.
Just 1 second. Let me try.
So you're supposed to be able to share screen right now because you're a co-host on both devices. Perfect.
Right. I think this works.
Perfect. So we'll start in 12 minutes, and you have these 12 minutes to prepare your talk.
Okay, thank you.
Алексей, можно будет вас попросить,
Да?
вот сейчас я думаю, наверное, начать следующий доклад, потому что я хочу быстро на перемене сбегать и
Хорошо, да.
построить доклад как можно больше. А если я побегу посреди доклада, то я смогу, конечно, начать и закончить, но сам доклад я не услышу.
Проблема. Хорошо. То есть вы закончите доклад? Вот,
Я этот закончу, потому что я хочу задавать вопросы, а следующий доклад, если можно,
тогда хорошо.
успеете, а я вернусь как раз вот на 3 минутки опоздаю, а потом буду вся здесь.
Хорошо, да, договорились.
Okay, let us reconvene. Are we all here, hopefully? So our next speaker is Ruihan. I will start again. Our next speaker is Ruihan from Louisiana State University, who will tell us about sharp analysis of Maryland localization and eigenfunctions for all parameters. Please start.
Oh, thank you. Yes, I want to thank the organizers for the invitation to speak at this wonderful conference, and I want to thank Mira for the introduction. Okay, so this talk is based on joint works with Svetlana Chitamerskaya and Fan Yang. Okay. So the main object of my talk is the 1D quasi-periodic Schrödinger operators. And that is given in the following form. And here, I should view this as a discrete Laplacian. This part is discrete Laplacian, and this part is the potential. And here alpha is the frequency. It usually comes from the physics magnetic flux, and the theta is the phase, and the lambda in front of the coupling, in front of the potential function is called a coupling constant. And we usually assume lambda to be positive. Okay, so this is our object. And there are some very well studied potential functions. For example, V is cosine function. Then one gets the almost massive operator. If V is a tangent function, then you get a Maryland model. And if V, and in general, V can also be an analytic function. Okay, there are also many studies on analytic potentials. And my talk is really about the Anderson localization. So what is Anderson localization? That is a pure point spectrum with exponential decay eigenfunctions. Then Anderson localization was first studied in perturbatively by Sinai, Frelich, Spencer, Vitever, and Eliasson. So what do I mean by perturbative results? Here I mean the largeness of the coupling constant depends on alpha. So the largeness depends on the frequency. And then around the 2000, and there were some non-perturbative results. And let's remove the dependence of lambda on alpha. And those were due to Chitamerskaya, Burgan-Goldstein, and the Burgan-Goldstein-Schlag. Okay, so there was some non-perturbative breakthroughs. So today I will focus on the non-perturbative approach to prove Anderson localization for quasi-periodic Schrödinger operators. So before I talk about the proof, let me introduce some tools that we use to study these operators. And if we look at the eigenvalue equation, you set H phi equals E phi for energy E, then you can rewrite it in the following way, right? You can rewrite it as phi n plus 1 phi n is equal to this 2x2 matrix times phi n minus 1. And then this 2x2 matrix, this E minus V negative 1, 1, 0, we are going to denote it by A theta plus N alpha. And this is called the transfer matrix. And then you have a dynamical system, right? So this linear skew product, alpha A, that act on the torus times R2 in the following way, right? So you map theta to theta plus alpha, and you map a vector x to A times x. And this dynamical system is called a quasi-periodic cocycle. And this is unique for the one-dimensional case. And in higher dimension, you lose this dynamical system point of view. And then why not like if you iterate this process? So here is links phi n plus 1, phi n to phi n minus 1. If you iterate this process, and you will get n matrices. Here is a product of n matrices times phi 0, phi negative 1, right? And we call this the product of the n matrices. We call it an theta. And that is the so-called n-step transform matrix. And this n-step transform matrix takes the vector at 0 to the vector at n. Okay. And then we can define the Lyapunov exponent. So that is the limit of 1 over n, the integral of ln norm of an theta d theta. So this is the Lyapunov exponent. So what it does is it characterizes the hyperbolicity of the transform matrix. And usually people would expect Anderson localization when the Lyapunov exponent is positive. And the matter is how you prove that, right? In the positive Lyapunov exponent region, right? How to prove that. And for the Maryland model, which is the topic of my talk, recall that the Maryland model is the one with tangent potential. Here you have a tangent function. And the Lyapunov exponent can be computed explicitly. I think this formula goes back to the original physics paper by Grampo, Fishman, and Branch. Okay, so it can be computed explicitly, and it is this L here and here, and it satisfies this equation. And you can see the right-hand side only depends on E and lambda, right? It does not depend on alpha. And we denote the Lyapunov exponent for the Maryland model. We denote it by L lambda E. And we also want to mention that for the almost massive operator, the Lyapunov exponent depends only on lambda, and it is for the almost massive with cosine potential. It is the maximum of 0 and log in lambda. Okay. So this is the Lyapunov, and I should also mention that for the Maryland model, the Lyapunov exponent is always positive. Right, this is always positive. So let me also talk about the continuous fraction expansion. Right, so given any irrational alpha, one can formulate its continuous fraction expansion like this. And if you, this is for irrational alpha, this is the infinite sequence of an. And if you cut it at an, at the position of an, you get a rational number Pn over Qn. And this Pn over Qn is called the continuous fraction approximate to alpha. And one can define index beta alpha to be, this is lim sup of ln Qn plus 1 over Qn. And by just some basic knowledge of continuous fraction expansion, one can realize it's the same as this one, right? Limit sup of negative ln Qn alpha, the torus norm of Qn alpha divided by Qn. So what does this exponent tell us? It tells us the exponential approximation rate of alpha. So why? Because if you just look at this expression, the left-hand side beta equals this guy, very roughly speaking, it tells you Qn alpha, the torus norm is approximately e to the negative beta Qn, right? So it gives you the approximation rate of alpha by rationals. And this rate is beta. In my talk, I'm going to call alpha is Diophantine if beta is 0, and alpha is Liouville if beta is positive. And I know that there are different definitions, right? But this is the definition in my talk. Okay, they only differ slightly. Okay? The different definitions. Now I'm going to describe the approach of the so-called green function expansion. So first, let's introduce one more definition. So this H restricted to a finite window x1 to x2. It is just the infinite dimensional matrix restricted to a window, right? Restricted to the window from x1 to x2. So that's a finite matrix. And given energy E, we define the green function to be, and the green function on the interval x1 to x2 to be just the inverse matrix. So here H is this matrix, right? It's a finite matrix, the inverse of that. So that is the green function. With the definition of green function, we have the following green function expansion. So given that a point y, here is x1, here is x2. Well, you can, if phi is a eigenfunction, if phi is a generalized eigenfunction, it does not have to be L2, right? But you can always expand it using this formula. So phi y is equal to green function times phi x1 minus 1 plus green function times phi x2 plus 1. So basically, using this, you can expand phi y in terms of x1 minus 1 and x2 plus 1. And remember, our goal is to prove Anderson localization. So here we would like to obtain an exponential decay upper bound for this green function.
I'm sorry, you want to obtain this exponential decay for which kind of alpha? Any alpha?
Yes, eventually we want to talk about any alpha. Yes, that's a very good point. But originally, yes, that's very good. Originally, people would expect it for Diophantine alpha, right? Where the small divisor is can be handled more easily. But in my talk, we will allow any alpha, even the most Liouville alpha. Yes, thank you. So, but the point is, we want to obtain such kind of exponential decay. If we have obtained such kind of decay, then we can just plug it here and plug it there, and then we are more or less done, right? Then we have some decay for the phi, right? So, but then the question comes down to how do we obtain such a kind of decay? And here actually, this you can write this G in terms of this P here I defined here. So let P be the PK, be the determinant of the finite matrix that we introduced. Here is H restricted to 0 to k minus 1. Be the determinant. And then by Cramer's rule, you can write this green function as P over P. Okay, on the top you have P x2 minus y, and in the bottom you have PK. Here K, let me remind you that K is the length of the interval from x1 to x2. And remember the situation is y is here, and you want to expand in terms of x1, x2. So plugging them in, right? This green function expansion becomes this, like this. And so now our object is to obtain exponential decay for these ratios. So what do we know about these P's? How do we study these P's? Actually, P is connected to the transfer matrix in the following way. So if you try to write down the n-step transfer matrix that we introduced in the beginning, then one can discover that this AN is roughly P, right? It's Pn, Pn minus 1, negative Pn minus 1, negative Pn minus 2. So the 4 components are all Ps, pKs. And then, remember, we want to consider this ratio. So this theorem nowadays is considered as a well-known theorem, and it actually gives you upper bound for the numerator. So what does this theorem tell us is, if the transfer matrix is a continuous matrix, and then you can bound the upper bound norm of the transfer matrix AN by roughly n times the Lyapunov exponent. So you can control the growth of the transfer matrix by the Lyapunov exponent.
And this is also for any alpha.
Yes, this is a hold for any alpha, and hold for irrational, I think. Yeah. But for the rational, I think it's more trivial. So, but yeah, it holds for any alpha. So what this theorem tells us is, since P is in the matrix, P is in AN, right? Those P's are elements in AN, and now you have upper bound of AN, then it gives you upper bound of the P. So in particular, this will allow us to get upper bound for the numerators. So now this theorem should give us upper bound for the numerators. Well, the difficult part is to get a lower bound for the denominator. So that's the difficulty. So the key is the lower bound for the denominator. So very naively, what should we expect? Very naively. So this is just very hand waving. So as we mentioned, this AN is roughly P, right? Very naively. So you would expect this log n 1 over n log in Pn is roughly 1 over n log in the norm of the transfer matrix, which you would expect for most of theta. For most of theta is close to the average. And what is the average? Average is roughly the Lyapunov exponent. So this is very roughly, and you see in particular there is a red tilde here, which means it's not going to work like this, right? But very roughly speaking, you would expect this to be true. And then what it gives you is so not only you would expect not only the upper bound holds, this Pn should be roughly of that size. I see a chat. Let me. The Maryland model. Yes, I think the Maryland model is called the Maryland model because Granpol, Fishman, and the Branch, they were at Maryland, if I remember correctly. So that's why Barry Simon called it the Maryland model, if I remember correctly. Yeah. Okay. So and then one can, well, if this is true, then perfect, right? You can plug it into the denominator, and remember we have numerator and denominator, then everything's done. This is you have exponential decay. But this is too good to be true, right? Things cannot be so easy. However, what I said here is it's just not correct, right? It's too rough. So this is a picture that I took from Wilhelm Schlag. And so what is this picture? This is n, capital N equals 100. So that is basically 1 over 100 of log of our transfer matrix A100 theta. So this is a plot for that. And you see a subharmonic feature of this object that we are studying, right? And in particular, it has large deviations in the lower bound direction. So here you see it drops very deep. It has a very deep drop. And on an exponentially small set, it has a very deep drop. And those deep drops make the lower bound hard. Right? So in general, you cannot expect for any theta the lower bound holds because it's going to drop very deep on a small set. Then how do we obtain the lower bound? So here let's recall the almost massive operator where V is cosine. And in 1999, Chidamar-Skaya has this remarkable lemma, which says that the Pn has some structure. So she proved that the Pn is actually a polynomial. This is crucial, is a polynomial in cosine of degree n. This degree is also crucial. So this is very crucial, and degree is also very crucial here. So using this lemma, this remarkable lemma, and she combined it with Lagrange interpolation theorem, which tells us that the absolute value of Pn, well, it cannot be too small at n+1 uniformly distributed points, right? If it's too small, then the Lagrange theorem tells you it must be uniformly small, but that contradicts with Lyapunov exponent lower bound, right? And then she used this to eliminate the so-called double resonance. So she showed that this cannot happen combining them. It basically tells us if Pn is small, near k equals 0, which is the center, right? Then Pn cannot be small, cannot be uniformly small when k is near n. Then this Pn must have a proper upper bound when k is near n. And this is the lower bound one can insert into the Green function expansion and prove everything from there. So of course, this is too rough, and one have to be careful about this too small and uniformly distributed and the appropriate lower bound. So all these need to be proved quantitatively, and the proof is very technical. But this is a very rough idea of how that works. So actually, she proved that in 1999 that there is a metal insulator transition for the almost massive operator, and for all Diophantine alpha and almost every theta. So she proved in particular the Anderson localization for lambda greater than 1, and for all Diophantine alpha and almost every theta. And I have to say, most of the recent work on the almost massive operator are all built on this work she had in 1999. Okay. So this is how one deal with the almost massive operator, and this lemma is very crucial here. So what about the analytic potentials? Well, the analytic potentials, then one have to use some structure of this. So what is this set? This set is roughly speaking where the lower bound does not work. A proper lower bound does not work, does not hold. Okay, because it says that this quantity is less than E minus n to the negative sigma. So that is a bad set. That's a large division set that we saw in the picture before. And then using the structure of this set, and in particular the semi-algebraic set structure, Bergan, Goldstein, and Schlag, they were able to prove Anderson localization for analytical potentials. Okay, so this works for analytical potential, but there is a price you have to pay for that. They have to delete some alpha, and this alpha gets deleted implicit. Okay, so for example, to my knowledge, one don't know if Anderson localization hold for the golden mean, right? So for a particular alpha, I think they cannot prove Anderson localization. So they have to delete some set of alpha, which is implicit set of alpha. So that's the price you pay for the analytic potential. And then let's finally get to the Maryland model. Yeah. And this Maryland model was proposed by Grampo, Fishman, and Branch, and as a linear version of the quantum cake router. And here you see that for the quantum cake router, you have n square alpha. They linearize it and have n alpha here. Okay. Well, the Maryland model actually was, for the, in particular, the Anderson localization for the Maryland model was proved very differently from what I just described, the green function expansion. It was proved using a completely different approach called the Cayley transform. What is a Cayley transform? It is the following. I don't think I have time to go through it. But let me just say that using Cayley transform, you can reduce the Maryland model to solving a cohomological equation like this. Right? So you can reduce it using the particular feature of the Maryland model for the tangent function. It works particular for tangent function. And you can reduce it everything to solving a cohomological equation. And so if this C, you can prove it has analytic solution, then C hat has analytic solution, then it implies the Fourier transform C has exponential decay. And then you can go back to the eigenfunction you start with U. Go back through this transformation. Okay. So it was handled very differently. And using the Cayley, I think also the Cayley transform goes back to the original Grampo, Fishman, Branch paper. Right? So using this Cayley transform, Barry Simon was able to prove that for all Delphinting alpha and for all theta, the Maryland model has Anderson localization. So this was the result in 1985. And then quite recently, in 2015, Chidamskaya and Liu, they were able to push it to the sharp region. So they defined the following index delta. And this index was defined, this appears through the Cayley transform, right? So they defined this index delta alpha theta, and they proved that this the Maryland model has pure point spectrum for Lyapunov exponent greater than delta, and has purely singular continuous spectrum if Lyapunov exponent is smaller than delta. And let me also say that this delta alpha theta, it is in general is less or equal to beta. So the beta that we defined earlier in the talk, and it's actually equal to beta for almost every theta, but not for all theta. Okay. Then the question is, can one use green function expansion to study the Maryland model? The answer is yes. And this was done by my collaborators, Chidamskaya and Yang, in 2017. They were able to come up with a green function approach, green function expansion approach to the Maryland model. So they proved that, again, for Delphinting alpha and all theta, H has Anderson localization. Well, the strategy they use is similar to Chidamskaya's approach in 1999. Well, the key is, remember, for almost massive, the key is to write this Pn as a polynomial of cosine. Here, they were able to write P for the tangent potential, write it as a polynomial of a tangent. And again, it's a degree n. This degree is also important. And actually, it was not clear whether it can be, whether that can work here, right? Because for the Chidamskaya's proof, it relies on the cosine feature, right? So it was unclear whether it can be done here, but they were able to do it. Now, then the question is, here is Delphinting and Delphinting alpha. Can one further extend this approach to the sharp region? That's the question. And there are some serious difficulty here to extend it to the sharp region. And now let me spend a few minutes to talk about the difficulties. Well, if one can overcome some difficulty on the technical level, one can adapt the strategy of a more recent paper by Jittemer Liu on the almost massive operator, where they proved when log lambda greater than beta alpha, Anderson localization. Okay, so where they proved when the Laplace exponent beats beta, the almost massive operator has Anderson localization. So if we try to adapt their strategy, it works, but it works in this region. So one can adapt their strategy to cover the region where the Laplace exponent is bigger than beta in the Maryland model. And the eigenfunction decay is here, is e to the negative Laplace exponent minus beta. But for the Maryland model, this is not the sharp region. There is a remaining region when the Laplace exponent is less or equal to beta, but greater than the delta index. Remember, delta in general is less than beta. So one can make that part work, but there is a remaining region here. And this is a part that requires completely new ideas. Because one need to break the so-called beta barrier. Okay. So now one need to, the Laplace exponent have to go below beta. Okay. Then where does beta, I want to describe where does beta even appear? Why does beta enters? Why does beta alpha matters? Because because beta actually characterizes the uniformly distributed behavior of the sequence of theta plus k alpha. And then it enters the localization computation at the strength of resonance. Okay, if beta is larger, then you have a stronger resonance. And in general, one would expect Anderson localization when the hyperbolicity of the transform matrix, which is the Laplace exponent, beats the strength of resonance. And this is actually what was done in Jittemer Liu's paper, where they proved the Laplace exponent beats beta alpha, then almost massive operator has Anderson localization. Okay, so you would expect Anderson localization when Laplace exponent beats the strength of resonance. In this case, for the Maryland model, the strength of resonance is beta alpha. However, in the remaining region, the strength of resonance is too strong that it beats the Laplace exponent. And how to make Anderson localization work? How to prove Anderson localization? The thing is, we have to find an additional factor to bring the exponential decay rate of the eigenfunction down from beta, here you have beta, down to delta. So remember, previously one can prove this is the decay rate, but when beta is large, this decay rate may be positive, right? So it's not really a decay. So one has to find an additional factor to bring it down to delta. The challenge lies in finding this additional factor. And then what we realize is there is a so-called phase anti-resonance. Okay, so the resonance now is very strong, but there is some anti-resonance factor introduced by the phase theta that eat up some of the resonance strengths and allow you to prove Anderson localization from there. So for the Maryland model, actually this green function, as we see, is P over P. There is an additional product of cosines hiding in the Maryland model. So you can write it as product of cosine, then P tilde over P tilde. I would say that P tilde is regular. Okay, I don't have time to explain what is regular, but there is this hidden product of cosine. And then the question is, can we use this product of cosine to eat up the resonance to help us to prove Anderson localization? And how does one connect this product of cosine to the delta index that we have seen before? So one of the key is we have to find an alternate expression for delta, because in the previous expression, it's not clear at all how it's connected to eigenfunction expansion, right? Because that came from the Cayley transform, and so it was indirectly related. So here we have to find an alternate expression, and we are able to do that. And you see this delta is roughly this index, and what is here is this is just beta. And here you have additional cosine. And it turns out very roughly speaking, this minimum of cosine using our new expression for delta, it is e to the delta minus beta qn. Well, then you see some hope, right? This is the additional factor. And this is very small when delta is less than beta. Right. And then you see some hope, because if this product happen to contain this minimum value, this is just a minimum one, then perfect. If it contains the minimum one, then it's perfect, because this minimum one is going to provide you the additional factor decay. And that happens in some simple cases. In some relatively simple cases, this product cosine happen to contain the minimum one, and everything is good. But unfortunately, there are some difficult cases where the minimum guide does not appear in the product of cosine. But you may not go through a minimum of cosine, right? When you do the green function expansion, it depends on the position, right? So there are some difficult cases where it's not easy, right? It was unclear where the additional factor come from. So then it turns out we can prove this very key estimate for the upper bound. So this is our breakthrough, the major breakthrough in our paper. Is in the difficult cases, it does not come directly from the product of cosine, but it actually comes from an improved upper bound of P in the numerator. And this proof relies crucially on the unbounded feature of tangents.
My apologies, but it seems like this lemma is only for the Liouville alphas.
Right, exactly, yes. This is for Liouville. Because for Delphinting alpha, it's already young already.
So you wanted just to close the gap of Liouville.
Right. Yes, I want to close the gap for Liouville. And in particular, I want to prove it for any Liouville, even for beta equals infinity. And you see when beta equals infinity, the most Liouville case, you have better decay here. Right? Yes. So this is the improved upper bound. Why do I say the improved? So this part is the standard, the Lyapunov exponent. But there is an additional factor here, e to the delta minus beta. And one should compare with the standard numerator estimate where one simply have Lyapunov exponent. So this is the additional factor that we are looking for. So and then we can fill in the gap, right? Exactly fill in the gap and close up to prove Anderson localization for all the parameters in the sharp region. And I have 2 more minutes. Let me summarize my talk and give an outlook. So what we did is we developed an alternative approach to Anderson localization for the Maryland model. But then the question is, well, the Cayley transform already took care of the Anderson localization. Why do you need an alternative approach? Well, the answer is we can use this green function expansion approach to study the asymptotic behavior of the eigenfunctions. And furthermore, we can use it to study the local fine structure of the Maryland eigenfunction. Okay, this was done previously for the almost massive operator by Chitomaska and Liu in their paper. So here we can, the green function approach allow us to do that. And this is our forthcoming upcoming paper. Right? So this is number one. And secondly, if you look at the Cayley transform, it's clear that it relies on the crucially on the tangent. So it cannot be applied to other unbounded models. For example, there is a model called the GPS model, where V is cosine minus 1 minus tau cosine, right? So the Cayley transform does not apply, but it's still unbounded when tau is greater or equal to 1. And our approach has a potential to deal with that and possibly deliver some sharp results on that as well. And further, not only unbounded potentials, there's some link between unbounded potentials and singular Jacobi matrices. So unbounded means on the potential is unbounded. A singular Jacobi means when the off-diagonal sampling function has zeros. So there are some link between them. And for example, the singular extended Harper model. There is a extended Harper model in a singular region. And again, Cayley transform clearly does not apply to that, but our approach can be applied there. So that's why we developed this alternative approach. And so let me just spend 1 more minute to say about the structural eigenfunction that we find using our approach for the Maryland model. So sorry, I drew this picture this morning, so it doesn't look very good. So this is what the eigenfunction look like. Yeah. So here around 0, you see this is eigenfunction. I didn't draw the left-hand side, but this is around 0. So on the around 0 is normal. It's the standard eigenfunction. But so this is Qn. But when what is this point here is the minimum of cosine. So when it hits the minimum of cosine, sorry, yeah. 1 more minute. When it hits the minimum cosine, then you see the eigenfunction has a sudden drop. You can see there is a drop from here to here, or possibly the other points. So this is the first new feature of the eigenfunction that we proved. And also you see that depending on the parameter exponent and beta over 2 and beta, the eigenfunctions can have different structures. And they are in total 4 different cases. And so this is what we can prove using the green function approach. So you can see very fine structures, local structures of the eigenfunctions using our approach. Okay, I think I will stop here. Yeah, thank you.
Thank you very much. Let us thank Bree. Are there any questions? Yes, Anton.
Hi, Rui. Thank you for the nice talk. I wanted to ask you, you were talking about Anderson localization. Maybe I just missed, maybe you mentioned that. What do you know about the topological structure of the spectrum for Maryland model?
Yeah, that's a very good question. I didn't put it in the talk. Yeah, the spectrum is a whole real line. So there are no gaps. Yeah, because there is no resonance. I wouldn't say there is no resonance, but because the tangent is monotonic.
Unbounded. It's unbounded. So
unbounded and monotonic. So using those 2 features, actually, I think it's definitely in Barry Simon's paper. I don't know if it's in earlier papers, but the spectrum is a whole real line. Yeah.
Yeah, it's if I'm not mistaken, already Barry writes that it's more or less direct consequence of the fact that they were talking about unbounded potential.
Right. You need unbounded in 2 directions. It goes to negative infinity and it goes to positive infinity. So yeah, they have to use that. Yes, I agree. Yeah.
I have a question. Can you say something about dynamical localization?
Yes, I think that's a very good question. of course, it only makes sense to talk about the local dynamical localization. So you only restrict your attention to the energy E, where the Lyapunov exponent beats delta. And I think that should be, I don't see why it is not true, because it's always the case, right? If you have Anderson localization and you know the eigenfunction decay, then you can expect dynamical localization. But I admit we haven't looked into it.
You haven't?
I think, yeah, I think it's true.
Mm-hmm.
I think it must be true, yeah. But we haven't looked into it, yes.
So right now, your piece, which deals with Liouville alpha, basically closes the question for any alpha.
Right. So it holds for any alpha and any theta. Yeah. And yes. So it has. But I would say you can theoretically also consider what happens if they are equal. What if a Lyapunov exponent is equal to delta? And I know there are some recent work by Avila, Jimmerskaya, Zhou, and they have works on the transition line, exactly on that line. Yeah, but I think that's also a possible project to do, right? But this basically fills all the parameters except on that line.
Okay. Are there more questions? If not, then let us thank our speaker again. Thank you very much, Rui. And we will reconvene in 14 minutes when Anton will present his talk, and this will be the last talk of the conference. So hopefully Anton also will say a couple of words at the end. Okay, we will see you all in 13 minutes.
Yes, thank you for coming to my talk. Yeah.
Thank you. Леша, вот я сейчас убегу, и я надеюсь, что я вернусь не больше, чем на 3 минуты опоздаю, но, пожалуйста.
Да, все сделаем.
Я просто хочу послушать доклад Антона, и поэтому не хочу убегать посредине. Спасибо.
Ира, сделайте, пожалуйста, Антона с организатором.
Я не уверена в том, что это я могу делать.
Нет, у нас тут еще Ира сидит, как студентка.
Ира. Вы сказали Ира, я услышала меня. Я просто
нормально.
задержалась на минуту, чтобы увидеть, что от меня ничего не надо.
Антон, добрый вечер. Можно слайды попробовать показать нам?
Доброе утро. Сейчас попробую.
У вас утро, да, Антон?
У меня 9 утра.
А?
У меня 9 утра.
Вот так, доброе утро. Здорово.
Доброе утро.
А у нас 8 вечера.
Все ли видно, Алеш?
Да, все видно, прекрасно.
Отлично.
Антош, привет, ты тут?
Привет, Маша, я тут.
Привет, привет.
Привет, я вот все.
Это я. Ой, а это она. Да,
Я, я вот пытаюсь сделать так, чтобы когда я
Привет, Леша.
шерю скрин, то я все еще видел вас, а у меня как-то это не получается.
А зачем тебе нас видеть?
Ну, как-то приятно.
Ага.
Лучше мы, Антон, на вас будем смотреть. Добрый вечер, это Сергей Пелевин.
Добрый вечер, Сергей.
Ну, у вас не вечер, но я не знаю, где вы географически сейчас, поэтому...
Я в Калифорнии.
Ну, тогда у вас не вечер.
Не вечер, но добрый, да, Антон? Привет.
Здравствуйте, здравствуйте.
Здравствуйте, Антон. У вас там тепло?
У нас сегодня жарко, обещают 30
Вот
градусов.
так.
30 градусов. А как вы вообще там живете?
Караул.
Вот вчера было холодно, дочка даже кофточку одевала в школу.
Да, 25, да?
Ну, где-то, да.
Я не в кофточках. Вот ведь до чего дошли. У нас он 0, у нас еще и -6 уже было даже.
У нас зима начинается, у нас здорово.
Уже снег лег немножко.
Главный признак зимы – меняем колеса на зимние.
Я вот хотел приехать, но не получилось, к сожалению. Все,
Не получится, да, Антон?
Нет, ну локдаун же ввели, так что теперь все.
Где ввели? А где ввели локдаун-то, Антон? У нас или у вас?
В Москве. Ну,
Там
вообще.
вводили, да, сейчас непонятно, что, в общем, то ли есть, то ли нет. Как бы что-то можно делать онлайн, что-то офлайн, что-то нельзя. В общем, какая-то загадка.
Ну, это как кому?
Ну да.
Вот мне ничего нельзя делать офлайн, поэтому мне проще.
Ну, я тоже не очень поняла, что нам разрешили. Сказали, типа, студенты могут приходить, бронировать аудиторию, даже встречаться с преподавателем, но только это не должно быть как занятие проведено. Я говорю, о.
И не сказали, что это должно быть.
То есть приходит инкогнито. Главное, что они не знают.
Вот единственное, когда смотришь на эту конференцию, ты понимаешь, что так вот не соберешь столько, такая мощная конференция, да, так это, конечно, не наедет столько народу. А тут, конечно, фантастика просто.
Ну, это Алексея надо благодарить в первую очередь.
Алексей, да, всех, молодец. Это вообще фантастически. Причем это все остается, можно послушать, потому что подряд, конечно, тяжело, но действительно это настоящий такой вдруг реклама, что происходит сейчас в мире. Это здорово, динамическая система. Да, это, пожалуй, не соберешь ни на одну конференцию.
Ну, раньше вот собирали все равно.
Ну, собирали, но это вообще уникально. Другое дело, что не заменить абсолютно. Раньше какая-то радость была у математиков. Поехать куда-нибудь. А теперь сидишь онлайн. И чего?
Радость на факультет поехать.
Да, да.
И встретиться тайно со студентами.
Заведующего можно увидеть воочию. Здравствуй, Оля.
Здрасте, здрасте. Ну, это раз воочию.
Hello, Ransom, nice to see you.
Какие у тебя там цветочки сзади?
И журавли. Вон, как.
Good evening.
Good evening. Так, все, не будем мешать. Да.
Все.
Dear colleagues, it's my pleasure to introduce the last speaker of our conference, Anton Gorodetsky from University of California in Irvine, and he'll talk about anti-classification results in smooth dynamics. Please.
Thank you very much. So I would like to thank the organizers for the invitation. I remember, I believe it was the last conference where Anosova was participating. It was in Moscow and Stiklov Institute. And it's a great pleasure to participate in this memorial conference, and a little bit sad that it's a memorial conference, not just a birthday conference. Today I'm going to talk about the results that on the first glance are a little bit away from the topic of the conference, but as you will see, it's actually very close to the main ideas that people are studying in dynamics, very close to the idea of structural stability and so on, and very close to the fundamental paper by Smale where all those questions were proposed. So I'm going to say that the project that I'm going to talk about is joint project with Matt Foreman. I believe he was here, but anyway, I wanted to show how he looks like in real life. And one of the purpose of this talk is certainly to explain our results, but another one kind of hidden purpose of this talk is to advertise the collaboration with people from descriptive set theory. I believe that the amount of questions, very natural and beautiful questions, is enormous. And what we're doing here is essentially just scratching the surface. So I want to start with talking about some problems in mathematics that cannot be solved. I will just remind several. So for example, squaring the circle. What you do, you take a circle of radius 1, and the task is to construct a square using just a compass and straight edge, such that the area is the same. So in modern terms, it means that you take the area of the circle and you want to find the square with the side root square of pi. We know that root square of pi is transcendental number. We know that anything that you can construct using the compass and straight edge must be algebraic number. So this problem is unsolvable. Interestingly, this problem was so popular that it became a symbol of something that is mysterious, unsolvable, and so on. And even in one of the books of Carl Jung, you can see the pictures related to squaring of the circle as a symbol of a mystery. Another problem that is certainly known to everybody here is angle trisection. So once again, you take an angle, and using the compass and straight edge, you need to cut this angle into 3 equal parts. Everybody knows how to cut it into 2 equal parts, but it turns out that not every angle can be cut into 3 equal parts using these tools. And this was shown by Pierre Wansel in 1837. Actually, there is an algebraic approach that uses Galois theory, but Galois paper was published a little bit later, and this was the first proof. And of course, that list would be absolutely incomplete without mentioning Abel-Ruffini theorem. If you have a polynomial of degree 5 or higher, it's impossible to express the roots using just a formula that uses radicals, not any special functions. And Ruffini provided the first but incomplete proof, and then Abel completed that proof, and it was known in the beginning of the 19th century. So what I would like to mention is that in spite of the fact that each of those problems was unsolvable, the proof that it's unsolvable by itself had huge influence to the way people started to think about the corresponding objects, and it was a motivation for lots of research and new notions and new problems and so on. So today I'm going to propose another question that I want to add modestly to this list. The question is whether we can classify dynamical systems. Well, of course, in this form, this question is way too broad. We need to specify what exactly do we mean by that. So let's restrict ourselves to smooth dynamical systems. So let's take a smooth manifold. Let's consider the space of all diffeomorphisms of class of smoothness C infinity. And what I want to find a reasonable classification of all diffeomorphisms. So once again, what does it mean to find a reasonable classification? Whenever you want to find a classification of any kind of objects in mathematics, you want to say up to what equivalence relation you want to classify those objects. So if you classify matrices, for example, you want to say something like, I want to classify matrices up to, so I want to consider similar matrices as the same. So this is our equivalence relation. And then you come out with Jordan normal form and something like that. So we're going to classify diffeomorphisms with respect to topological conjugacy. So it means that two diffeomorphisms are the same for us if there is a continuous change of coordinates such that it sends one diffeomorphism to another. So why continuous change of coordinates? Why not smooth change of coordinates? It would be much more natural, naively, if we acted on diffeomorphisms also by, so the space of all diffeomorphisms form a group, and why not to take a conjugacy by the elements of the same group? This question also makes sense, but it makes sense to talk about topological conjugacy, and that's what Smail specifically wanted to do, exactly because the initial motivation was to study structurally stable diffeomorphisms. If you want to study structurally stable diffeomorphisms that do not change the dynamics under the small perturbation, you don't want to consider smooth conjugacy because of the following reason. If you consider multipliers of periodic orbits, just think about the sphere, for example, where you have just one attractor attracting fixed point and one repelling fixed point. Then if you make small change of, small perturbation of the diffeomorphism, dynamics doesn't change if you allow continuous change of coordinates. But it does change if you allow only smooth change of coordinates, because in this case, multipliers are going to be, you can change the multipliers, and multipliers are going to be invariants of the smooth conjugacy, because the differentials at the fixed points are going to be similar, given by similar matrices. All right, so let me give some examples of successful classifications, just to get some intuition what we mean by classification. So if you consider all the Bernoulli shifts, then and up to isomorphism of measure-preserving transformations, then it's known, and this is a famous Arnstein theorem, that entropy is the only invariant of classification. So two Bernoulli shifts are isomorphic if the entropy is the same, and not isomorphic if the entropy is different. Sinai worked on that as well, and the final step was done by Ornstein. Another example from linear algebra, I mentioned already, if you consider square matrices, then up to similarity, Jordan normal form provides a classification. So if you know the sizes of Jordan cells, and if you know the eigenvalues that corresponds to each of the Jordan cells, this is a collection of numbers such that if those collections of numbers coincide for two different matrices, then those different matrices are similar, and if not, then not. So in both of these cases, you have classification by a number or collection of numbers. So you have numerical invariants that completely classify the objects. Or an example from algebra. If you consider finitely generated abelian groups, then it's known that every such group can be represented, can be is isomorphic to a direct sum of primary cyclic groups and infinite cyclic groups. So if you know the number of infinite cyclic groups and the orders of primary cyclic groups, then this is a collection of numbers that must coincide in order for two groups to be isomorphic. And if they don't coincide, the groups are not isomorphic. So this is a complete invariant. So let's now give an example from dynamical systems. I believe that something like that was already mentioned in this conference at some point. So let's talk about Morse-Male diffeomorphisms. Those are structurally stable diffeomorphisms that can be defined in the following way. Non-wandering set is hyperbolic and consists of finite number of fixed points and periodic points. And invariant manifolds of any two periodic points must intersect transversally. So in this case, you can try to obtain a complete classification, and in lower dimensions, in dimension 2, in dimension 3, such classifications were obtained. So the invariant in this case is some kind of graph, sometimes colored graph, and if those two finite graphs are isomorphic, then diffeomorphisms are topologically conjugate, and if not, then not. So once again, it provides a complete classification in that case. So what's important here is that Morse-Male diffeomorphisms are structurally stable, and so there are only countably many equivalence classes. So this is something that is different from the situation when you consider all the diffeomorphisms. Another example also from dynamics. Let's consider diffeomorphisms of a circle. Let's consider orientation preserving diffeomorphisms. In this case, you can define the rotation number. So even if it's not a rotation, each point will be moved and kind of rotated by some angle, but the angle will depend on the point. If you consider an orbit, then the average angle of rotation is well defined and doesn't depend on the point. That's the rotation number introduced by Poincaré. It's known that if this number is irrational, then for smooth diffeomorphisms, it means that the diffeomorphism is conjugated to the rotation with the same rotation number. And therefore, for diffeomorphisms with irrational rotation number, the rotation number is the only invariant. For the diffeomorphism with rational rotation number, in this case, the situation is slightly more difficult because you do have periodic points, and therefore you can consider 2 points in that periodic orbit for two different diffeomorphisms. And then the question is whether the corresponding, if you take the corresponding power of the diffeomorphism, the question is whether two corresponding homeomorphisms of an interval are topologically conjugate. It turns out that it's not that hard to classify all the homeomorphisms of an interval. So you know that there is a set of fixed points, it's some closed subset of an interval, and there are intervals in the complement, and for those intervals you either go to the right or to the left, so you have to assign plus or minus to each of the intervals, and that object can be classified. So interestingly enough, that accurate description of the classification was done by logicians, not by dynamicists, but anyway, such classification is possible. Okay, now what I want to try to fool you and to present a classification of all the diffeomorphism for arbitrary manifold. So let's take arbitrary manifold. So what I want to present an invariant. I want to present a function on the space of diffeomorphism such that if that function takes the same value on two diffeomorphisms, then those diffeomorphisms are conjugate. If different values, then those diffeomorphisms are not conjugate. So here's what I'm going to do. The cardinality of the set of all diffeomorphisms is continuum, so the same as the cardinality of real numbers. The cardinality of the set of equivalence classes up to the topological conjugacy is also continuum. So you have some set of cardinality continuum, which means that there exists a bijection between that set and the set of real numbers. Well, let's denote this bijection by phi, and here it is. Here is a function on the space of diffeomorphisms such that it sends two diffeomorphisms to the same number if and only if those two diffeomorphisms are topologically conjugate. Here's a classification. Well, of course, you will immediately say that this is not a classification because it's completely useless. Existence of this function is absolutely doesn't give us any tool to actually apply it to understand whether two given diffeomorphisms are conjugate or not. So of course, what's presented here cannot be considered as a classification, and therefore we have to be a little bit more careful when we say what is a classification by an invariant. So this is not a classification. Then the question is, what is a classification? So the question that we want to ask is whether there exists a complete set of numerical invariants, and what does that mean? What I want to ask the question whether there exists a Borel function on the space of diffeomorphisms with this property. So it takes the same values exactly on the diffeomorphisms that are topologically conjugate. Now, you can say that Borel functions form a huge class of functions anyway, but notice that what we're planning to do that such Borel function does not exist, and therefore the more general class of functions we allow here, the better the result. So Borel function is pretty good. But once again, why exactly the Borel function? First, let me give you some examples of Borel functions on the space of diffeomorphisms that give you some invariants that come to your mind if you want to characterize a diffeomorphism in some way. For example, if you consider the number of fixed points of a given diffeomorphism, then it's a Borel function on the space of diffeomorphisms. If you consider the number of periodic points of a given period, then it's a Borel function on the space of diffeomorphisms. If you consider the rate of growth of the number of periodic points, then it's a Borel function on the space of diffeomorphisms. Topological entropy is another example. You can take those functions and unite them into one. So what you can do, you can associate with each diffeomorphism a sequence of numbers. Each number is a number of the corresponding of the periodic points of the corresponding period. So that will be a map from the space of diffeomorphisms to, roughly speaking, n to the power n, which is actually homeomorphic to the set of rational numbers. This function is a Borel function. Transitivity, minimality, topological mixing, any other property you can think of, you can say it's not a function. You can consider that as a function to the 0-1 set. 0 if the property is not there, 1 is if the property is there. Each of those functions is a Borel function. So heuristic principle is that everything that you can define either as a property or as a function of a diffeomorphism, as a number that you can assign to diffeomorphism, as soon as you don't use something exotic like axiom of choice, the chances are you will define the Borel function. Because just by definition, when you define something, you have to describe it, and the description by itself defines, can be expressed as kind of some set of operations. So you take some open sets or complements or intersections or unions, you will get a Borel function anyway. So the first theorem, the first result that I'm going to talk about is the following. For any manifold of dimensions that is at least 2, you cannot find a Borel function on the space of diffeomorphisms such that it provides a classification. It's impossible to classify the diffeomorphisms by numerical invariance. So you can ask at this point, why do we consider the function to the set of real numbers? Maybe we have some more complicated invariants. Maybe we have some classification by some functional invariants. Maybe we have some classification by, I don't know, points in a Hilbert space, something like that. Well, let's introduce a notion of a polar space. A polar space is a topological space that is homeomorphic to a complete separable metric space. So whenever people encounter that, they ask why not just to define the polar space as a separable metric space. It's because many polar spaces do not look like separable metric spaces. For example, the interval, open interval from 0 to 1 is a polar space because it's homeomorphic to the real line, but nevertheless by itself it doesn't really look like a complete metric space. Or the set of rational numbers. It's also a polar space. You can think about the set of rational numbers using the continued fraction expansion, and in this case, it's homeomorphic to n to the power n, to the space of all sequences of natural numbers. And that set, on that set, it's already not hard to introduce a metric which makes it complete separable space. But by itself, it really doesn't look like one. Hilbert cube, so lots of functional spaces. So this is a sufficiently large collection of different spaces. So, and that result can be improved. There is, as soon as you consider manifold of dimension at least 2, there is no Polish space and there is no Borel function from the space of diffeomorphism to that Polish space such that diffeomorphism would be topologically conjugate if and only if the corresponding images coincide. So how would you prove such a result? Of course, as usually in mathematics, you want to reduce the result to something that we already know. Unfortunately, in descriptive set theory, people know a lot about.
My apologies. May I ask, this version with the improved result, is it the optimal version with the Polish space?
What do you mean optimal? Optimal in what sense?
In the sense, what kind of restrictions on the space you have?
Let me put the answer in this way. The classification by an invariant is not the strongest, not the most general way to classify. So later I will talk about different, much stronger result that guarantees that there is no classification in another much stronger way. So if this answers your question. So. So, but first, let me talk about the proof of that result. So we want to reduce that to something that people in descriptive set theory do know, and they do know, for example, the following. If you introduce the following relation on the space of sequences of zeros and ones, the relation is the following. Two sequences are equivalent if they are actually the same, except maybe a finite number of exceptions. Or in other words, the two sequences are equivalent if and only if they have a tail which is the same. Okay, this is an equivalence relation on the space of all sequences. The space of all sequences topologically can be, you can think about it as about a Cantor set. So you have some equivalence relation on a Cantor set, and it's known that there is no Borel function on that space that would classify the classes of equivalence with respect to that equivalence relation. So there is no Borel function such that it sends two sequences to the same number if and only if those sequences are equivalent in that sense. And you can replace R by any Polish space in this lemma. Okay, so what we want to do, we want to reduce this statement to the statement about diffeomorphisms. So here's what we're going to do. A Borel reduction in this case is the following trick. Suppose you have two Polish spaces. Suppose you have some equivalence relation on one of them, and you have some equivalence relation on another space. We will say that the first equivalence relation is Borel reducible to the second if there exists a Borel function from the first space to the second such that 2 points in the first space are equivalent if and only if the images are equivalent. Notice that here we do not assume that our Borel function Xi is surjective. Moreover, it's enough to find a function into a tiny, tiny subspace of Y in order for that to work. But if you can find such a reduction, then it allows you to say that if one of the spaces is, if the second space, if the first space is not classifiable, then the second space is not classifiable by numerical invariance, because if the second space was classifiable by numerical invariance, then this function Xi would give you a classification of the first space. So in these terms, to find a complete set of numerical invariance means to find a Borel reduction to an equivalence relation, which is just an identity on some Polish space, right? So we want to prove that this is impossible. So what we actually prove is that for any manifold of dimension at least 2, there exists not just a Borel function, but a continuous function from the space of sequences to the space of diffeomorphism such that you can reduce the relation E naught to the topological conjugacy on the space of diffeomorphisms. So if we can do that, then we're done. Then if you had the classification by numerical invariance on the space of diffeomorphisms, that would give you the classification by invariant numerical invariance on the space of sequences 0, 1. 0 and 1 sequences, and that something that we know cannot be done. Great. So here is a construction, certainly not the only construction, but one that we came up with. What we're going to do, we're going to take a two-dimensional manifold. Let's think about a torus. It really doesn't matter, everything is local. And we're going to construct a bunch of diffeomorphisms. We're going to construct the function for each sequence of zeros and ones. We are going to construct a diffeomorphism that will be supported on the union of these disks, and everywhere else is going to be just an identity. So we have countable many disks on this picture, and I'm going to introduce countably many diffeomorphisms of disks such that those diffeomorphisms are pairwise different. They're not topologically conjugate. There are many ways to construct such diffeomorphisms. You can use periodic orbits, just the fact that if you have topological conjugacies and the orders of periodic orbits must coincide, you can use rotation numbers, you can use there are many ways to do that, and just choose your favorite. And let's assume that we already have countably many different diffeomorphisms. So we choose 2 points, we choose 2 sequences of disks, and then we are going to define a diffeomorphism for each sequence of zeros and ones. So the restriction is going to be we have the disks from below of the points A and B and the disks from above. So for the disk below, the diffeomorphisms will be exactly the same for all the sequences. So those are needed to make sure that if you have 2 diffeomorphisms that are topologically conjugate, then the point A and the point B are fixed points of that conjugacy. So those are kind of anchors that don't allow you to swap the points A and B by the conjugacy. Okay. So the interesting game happens in the disks above. And in the disks above, we will just distribute our diffeomorphisms somehow in the disks above the points A, B for the sequence that contains only zeros. Of course, we can do so in such a way that the norm C-infinity norm of the diffeomorphism becomes smaller and smaller sufficiently fast. So altogether, we define a smooth C-infinity diffeomorphism of the torus. And now what we want to explain how we're going to define the diffeomorphism for an arbitrary sequence. So let's consider 2 larger disks from above. If the first element of our new sequence is 0, we will do nothing. We will just keep the same diffeomorphisms as they were for identically 0 sequence. If the first element is 1, then we will swap them. So it will be the same 2 diffeomorphisms, but we will exchange the supports. For the second digit, we consider the 2 disks just below of a little bit smaller radius, and we'll do the same. If the element of the sequence is 0, we will leave them where they were. If the element of the sequence is 1, then we will swap them. And if you think for a minute, you will see that if you swap only finitely many times, then you get a diffeomorphism which is topologically conjugate to the initial one. But if you swap infinitely many times, then you definitely will get a diffeomorphism that is not topologically conjugate to the initial one. And that works for any 2 sequences. So for any 2 sequences, if you have the same tail, then it means that those diffeomorphisms are different only on a finitely many disks, and you can construct a topological conjugacy. You can move them around. But if you have those diffeomorphisms that are different at infinitely many disks, then it's hopeless. Then those 2 diffeomorphisms are not going to be topologically conjugate. And therefore, we found a continuous map from the space of sequences to the space of diffeomorphisms. And that proves that the space of diffeomorphisms is not classifiable by a numerical invariant. You can say that, well, the space of diffeomorphisms that we actually use is tiny, but that's quite okay, because we proved that in that tiny space, it's already non-classifiable, and therefore the space of all diffeomorphisms, which is definitely even more complicated, is definitely not classifiable by invariance. Right. But at this point, you can also say, okay, maybe we don't have numerical invariance. Maybe we cannot classify diffeomorphism even by functional invariance. But maybe there is some procedure that allows you to determine whether two different diffeomorphisms are topologically conjugate or not. Maybe it's not comparing the invariance. Maybe it's some other procedure. Maybe there is some list of questions you may want to ask about diffeomorphisms and then determine whether they are topologically conjugate or not. That would be good enough. So that would be a stronger type of classification. And it turns out, due to some technical reasons, I believe that those are just technical reasons, we need to increase the dimension of the diffeomorphism. And in this case, we can prove that if you have a manifold of dimension 5 or higher, then the equivalence relation given by the topological conjugacy, what is an equivalence relation? It's by definition a subset, symmetric subset. What is a relation in general? It's a subset in the square of the set. So the topological conjugacy is some subset of the space of diffeomorphism multiplied by the space of diffeomorphism. So the pair of diffeomorphism belongs to that subset if and only if they are topologically conjugate. So in the space, that set is not Borel. So equivalence relation given by topological conjugacy is not Borel. What does that mean? Intuitively, it means the following. Suppose that I allow you to ask infinitely many questions, countably many questions about diffeomorphism. So you construct some list. You can ask whether a given point will be mapped to a given open set. You can ask bunch of questions. You can ask about entropy. You can ask about periodic points. You can all the questions you can imagine all together. And you can analyze them simultaneously. So it's not like you ask one after another, but you have all the answers at the same time. It will not be enough to have the answers to all those questions in order to distinguish between, for given two diffeomorphisms, to distinguish whether they are topologically conjugate or not. So there is no such infinite list of questions. So that's essentially what it means, that it's a relation is not Borel. Or even stronger, actually, not just one list of questions. You can combine it in many different countable ways. So there are some examples of non-Borel equivalence relations in dynamics, but not in the case of smooth dynamics. For example, topological conjugacy on the space of homeomorphisms of a Cantor set is known not to be Borel. Topological conjugacy of the space of homeomorphisms of two-dimensional surface is also not Borel. If you consider ergodic measure-preserving transformation of an interval, for example, up to an isomorphism of measure-preserving transformations, then this relation is also not Borel. This is a result by Foreman, Weiss, and then Rudolph. Or even more amazing, you can consider isomorphism of measure-preserving transformation of a given manifold, say area-preserving or volume-preserving, but up to isomorphism of measure-preserving transformation. So the isomorphism doesn't have to be a continuous transformation. Isomorphism is just an isomorphism of measure-preserving transformation, as people do in ergodic theory. That isomorphism relation is also not Borel. And this is a recent result by Matt Foreman and Benji Weiss. So how one can prove something like that? Once again, we want to reduce the question to something that people in descriptive set theory already know, and they know the following. Let's define the space of all countable graphs as the map from n squared to 0, 1. So what it means that each natural number is a vertex of that graph, and for a couple of vertices, you just need to say whether the age between those vertices is there or the age is not there. So as soon as you have a symmetric function like that, it's exactly corresponds to our intuition of a graph. So one can equip this space with some natural topology that makes it homeomorphic to a counter set. And there is a natural relation on that space, namely two graphs are isomorphic if you can permute the vertices exactly in such a way that vertices connected by an edge will be mapped to vertices connected by an edge and vice versa. It turns out that this equivalence relation is not Borel. So this is something that we will take as a black box. This is known. What we want to do, we want to reduce that to our case, to the case of diffeomorphisms. What we want to find a Borel map, and actually we find a continuous map from the space of graphs to the space of diffeomorphisms, such that two graphs are isomorphic if and only if the images are topologically conjugate. If we can do that, then this reduction will show that the equivalence relation given by topological conjugacy in the space of diffeomorphisms is not Borel. Great. So how do you construct that? The construction is the following. First of all, let's associate each vertex of our graph to some point in R3. So I will start with three-dimensional space, but I will explain why we need two additional dimensions. Those points will converge somewhere, and we will choose those points in some very generic way, namely no 3 points will be on the same line, no 4 points are on the same plane, so there are no relations between those points. Then we will connect all those points. We will consider the complete complete countable graph inside of R3. So our choice guarantees that all the edges do not intersect each other. But now we want to code for each edge whether this edge is there or not in some dynamical way. So what I'm going to do, I'm going to take a small neighborhood of each edge, and inside of that neighborhood, I will define a diffeomorphism which is either makes the line between those 2 points attractor, or it makes it repeller. So it's clear in this case that any two maps where it's an attractor are conjugate to each other, and any two maps where it's a repeller are conjugate to each other. So in this case, we have essentially two building blocks, two maps. And what we're going to do, we're going to put a tiny neighborhood around each edge, and we will introduce the diffeomorphism inside of each of the neighborhoods, which is either attracting or repelling, depending on whether the corresponding edge is in the corresponding graph, is in the graph or not in the graph. So that, and everywhere else outside of those neighborhoods, our map is just going to be an identity. That defines a map from the space of graphs to the space of diffeomorphisms. You can certainly smooth everything out and to make sure that it's a C-infinity diffeomorphism. What we want to prove that in this case, any two isomorphic graphs will be mapped to topologically conjugate diffeomorphisms and vice versa. If any two diffeomorphisms of this type are topologically conjugate, then the graphs are isomorphic. So the second part is relatively easy. If you have a topological conjugacy, then it's induce some permutation of the vertices. And since it has to send attracting domain to attracting domain and repelling domain to repelling domain, it means that it sends vertices connected by the edge to the vertices connected by the edge. The other part is harder. Suppose you have two graphs that are isomorphic. How to construct a topological conjugacy? So the trick here, well, there are two tricks here. The first trick is to recall that any permutation can be represented as a product of transpositions. Well, we know that for permutations of finite set, but the same statement actually holds for permutation of natural numbers. We need to be very careful how we do that. We need to make sure that this representation by the product of transpositions is a convenient one in a sense, but I will not go into those details. Suppose we have such a representation, and suppose that we manage for an isomorphism, which is just a permutation of two vertices, manage to find such a topological conjugacy. Then what you want to do, you just want to take the composition of all those topological conjugacies, and you have to be very careful and put lots of accounting into proving that you have a convergence, and the convergence is actually a topological conjugacy as well. But let me first try to convince you that one can construct a topological conjugacy just for permutation of two vertices. So if you have permutation of two vertices, what you want to do, you just want to think about those two vertices as material points. You want to swap those material points. The problem is that in this case, some of the edges can intersect each other. Because if you take one point and you have another edge, another vertex which is fixed, then the edge, when you move one vertex, the edge will give you some two-dimensional surface. And two-dimensional surfaces in a three-dimensional space have tendency to intersect. Even in four-dimensional space, two-dimensional surfaces tends to intersect. Also, intersection is just a point, but you cannot remove it by some small perturbation. But in five-dimensional space, two-dimensional surfaces, if they are transversal, are not going to have any points of intersection. And that's a very, very rough explanation why we need extra two dimensions in order to swap two vertices in such a way that the edges can be extended homotopically in such a way that they do not interfere with each other. And then once again, there are many difficulties, technical difficulties that I am kind of hiding from you, but that's the main idea. Yes. Okay, I guess I should stop here, but I have just a couple of minutes. Do I have a couple of minutes left? Yes. So let me talk about some open questions. I remember the story about Dmitry Viktorovich Anosov. The story was the following. He was giving a talk at some conference, and he was reminded that his time is up, and only time for questions is left. And he said, "Okay, we only have time for questions, but no one ever said that the speaker cannot ask questions to himself. So I'm asking the following question," and then he continued. So I want to ask the following question. Well, I actually have some questions. So obvious question is. It's completely clear that the space of diffeomorphisms of two-dimensional manifold is huge and very complex. So our dimension 5 and that second theorem is obviously just an artifact of the proof. So how to reduce it to the dimension 2? Another question, which is also natural. We have C-infinity surgery that we implement here. And of course, it prevents that proof from working for analytic diffeomorphisms. Nevertheless, anybody who worked with analytic diffeomorphisms certainly confirms that the structure is extremely complex. You have Neuhaus phenomena there, you have everything you want. How to prove absence of classification for analytic diffeomorphisms? Once again, our diffeomorphisms that we're using is very degenerate. So maybe if we remove all those degeneracies, we will live with a very nice classifiable space. For example, let's consider just Kubka-Smil diffeomorphisms. Can we classify those? Or even more general, maybe it's possible to find a generic subset in the space of diffeomorphism which is classifiable. And moreover, if you consider C1 diffeomorphisms on a two-dimensional manifold, most likely the answer is yes, because the conjecture is, I don't know how far we are in proving that conjecture, but there were some improvements at some point. The conjecture is that structurally stable diffeomorphisms there form an open and dense subset. But I bet that if you increase dimension and increase smoothness, and the answer is different. We have classification of Morse-Males diffeomorphisms. And of course, there are Neuhaus domains and partially hyperbolic stably transitive diffeomorphisms that are extremely complicated. But what if we just restrict ourselves to the boundary of structurally stable, or even easier, to the boundary of Morse-Male diffeomorphisms? Is it true that the diffeomorphisms on that boundary are classifiable? Or not? I bet that the answer is no if you have sufficiently large dimension, but how to prove that? Another one, take your favorite class of diffeomorphisms, say minimal diffeomorphisms. This is a tiny class in the space of all diffeomorphisms, but I also suspect that those are not classifiable, and how one can prove that. Or you can impose some additional structures, say, let's consider volume preserving or area preserving diffeomorphisms. Once again, you have all these complexities. You have Neuhaus phenomena, you have persistent tendencies for those. Anybody who worked with those will say that there is no chance to obtain any reasonable classification. But can you prove that formally, not just as a hand-waving statement? So you can certainly continue this list, and the message is that there are plenty of interesting and natural problems here that people would be able to address if they start talking with people from logic and descriptive set theory. And that's where I want to stop. Thank you.
Let us thank our speaker. Great talk. Thank you very much. Are there any questions?
Can I make a question? Anton, what happened if, for instance, I guess that the only place that you use dimension 2 is when you construct these balls, when you have these the dynamics that you want. But for instance, if you restrict to one-dimensional maps of the interval as with critical points, I think that the result is the same or not.
If you consider non-invertible maps in one dimension, then even if you consider just quadratic family, the answer is not clear to me. I talked to Misha Lubich, and he said that from his point of view, it should be classifiable by an invariant. And he said that he knows how to prove that if MLC Mandelbrot local connectedness conjecture holds. He also believes that it's true even, and one can prove it even without it. But obviously, since no one asked that question formally, there is no formal proof available. I think it's a great question to some graduate student. If you consider one-dimensional maps from a larger class, I don't know the answer. I'm not even sure that it's a hard question, but I don't think that anyone ever thought about it really.
Because you only use the higher dimensionality in this step when you consider this family of small balls, if I understood correctly.
Yes, and in one-dimensional case, as soon as you try to repeat the constructions, they are going to interfere with each other.
Yes.
But it doesn't mean that some modification cannot work. I don't know.
Okay, thank you. Very nice talk.
More questions? Okay, then let us thank our speaker again. Thank you, Anton. And
thank you. And I would like to thank the organizers for all the efforts and time and bringing us all together. It's a pity we couldn't see each other in person, but I really hope that it will happen someday, somewhere, and we will continue our conversations. And I wish you all participants and organizers to survive and to meet with new and nice mathematics in the future. Thank you all.
Yeah, let us thank the organizers. This is the most important people in this conference. So I'm thanking Dorothy very much. It was a very beautiful conference, and I think everybody will agree that that we wish that these conferences would happen more often and more personal. I'm still complaining on Zoom. Thank you very much.
Thank you.
Thank you very much, and we are waiting here for you for the ICM 2022 for our satellite conferences, and we hope to meet in the next anniversary by Dmitry Viktorovich in person. Thank you very much.
Thank you. Bye.
Большое спасибо. Спасибо.
До свидания, Лешенька.
До свидания.
Всего хорошего.
Всем спасибо. Спасибо,
Спасибо.
Леша Клименко, конечно.
Всем спасибо, а самое главное здоровье. Здоровья и сил.
Всем здоровья, всем сил. Но зато в гостях побывали. Вон, смотрю, прям я вижу, как Сережа там книжки хорошие сзади, все стороны. Да.
Хорошо, я тогда выключаю, да?
Давай, всем
счастливо всем. А это будет где-то на YouTube, Леша?
Сергей.
Послушать можно будет потом это?
Несколько дней, да. А на сайте конференции там будут ссылки.
Антоша не хотел на тебя прийти, но он сейчас не мог. Вот он послушает в записи.
В записи все появится, там появляется.
За вчерашний уже есть.
Да, вообще здорово, конечно.
Супер, спасибо.
Спасибо всем.
Сейчас, Леша, кстати, извини, а просто вот текущая ютубная трансляция, разве не поможет, Маша?
Ну, наверное, да. Я не знаю только, сколько они будут хранить. То есть они вроде бы...
Они ее не хранят, они ее
прячут.
Они выкладывают с зумовских записей.
Поэтому, ну, по крайней мере, предыдущие дни я уже посмотрел в этих вот, в записях выложенных.
Да, Димочка.
Вот. Леш, ну ты выложишь на сайт, да?
Да, их там, ну, у нас специально обученные люди этим занимаются, они выкладывают просто на сайте конференции, там говорят, что уже к докладам там с понедельника по среду уже висят записи докладов.
Понятно, спасибо.
И, значит, это.
Спасибо большое.
Ладно, все. Всем до свидания.
Всем счастливо.
Счастливо.